And here, instead of saying that up to a third of the parties can be corrupt, we say something like no three of the possibly corrupt parties can cover the entire set when you take their union. So intuitively, the non-threshold setting is telling that the power with which an adversary can corrupt a party may not be uniform and may differ from party to party. So to understand this with more examples, MPC is possible in an asynchronous network as long as up to a third of the parties are corrupt. So if we have 5 parties, then one of them can be corrupt at once. And in a non-threshold setting, MPC is possible as long as the adversary structure, so this set Z here, is the adversary structure which explicitly mentions the sets of possible corruptions. And MPC is possible as long as this satisfies the Q2 condition, which means that if I take any 2 sets from this adversary structure and take their union, and that does not cover the entire set of parties. And with the example here, we are saying that P1 and P2 can be corrupted together, or P3, P4, and P5 can be corrupted individually. So notice that with the non-threshold setting, I can tolerate 2 parties being corrupt, and on the threshold, I could only tolerate 1. So immediately, it is slightly better than the threshold setting. But the downside of the non-threshold setting is that the adversary structure can be exponential. The size of the adversary structure can be exponential in the number of parties, and this might cause a communication blow-up. So MPC is possible in a synchronous network as long as up to half of the parties are corrupt. So if I have 5 parties, now I can tolerate two corruptions at a time. And with a non-threshold adversary, it's possible as long as the adversary structure satisfies the Q2 condition, which means that if I take any 2 sets from the adversary structure and take their union, then that won't cover the entire party set. So with this example, we are saying that P1, P2, and P3 can be corrupted together, or P4 and P5 can be corrupted individually. So notice here that with the synchronous network, we can tolerate more number of corruptions than we could in the asynchronous network, since we can tolerate up to half of the parties being corrupt. And so we look at the question of whether we can design an MPC protocol which works in both synchronous and asynchronous networks while giving the best possible guarantees in both networks. That is, we want to be able to tolerate more number of corruptions in a synchronous network than an asynchronous network. And the rationale behind this line of work is that networks may not be purely synchronous or purely asynchronous. At times they can be synchronous, at times asynchronous, and irrespective of the network type, we want to be able to give the best possible security guarantees. And prior work has looked at this for computational and perfect security, and we're the first to look at this with statistical security. And we show that it's possible as long as the Q2-1 condition is satisfied. So now we have 2 different adversary structures, the synchronous one, which lists out the possible corruptions in a synchronous network, and the asynchronous one, which lists out the possible corruptions in an asynchronous network. And the Q2-1 condition means that if I take any 2 sets from the synchronous structure and any one from the asynchronous structure and take their union, then that won't cover the entire set of parties. So that's the problem statement. And let's look at the solution now. I'll give a high-level overview of one part of our solution. So the parties want to compute a function in MPC, and they represent this function as an arithmetic circuit of addition and multiplication gates. And the protocol would be something like this. So each of the parties will secret share their inputs. And once you have secret shares of 2 input wires, you can compute the secret shares on the output wires. And this keeps going in a layer by layer fashion until you have secret shares of the output and you reconstruct these. So in order to come up with our MPC, we had to come up with a lot of building blocks and subprotocols for the network agnostic setting, but I'll specifically focus on our verifiable secret sharing protocol for this talk. And for VSS, we require 2 building blocks. The first is broadcast, which allows a sender to send a message uniformly over the network. And the second is an IC signature, which is a statistical or unconditional equivalent of a digital signature, which allows a signer to sign a value to an intermediary who can then reveal this value to a receiver. And the guarantees of the signature scheme are that the intermediary cannot reveal a value which was not signed by the signer, and that the receiver will not learn this value until the intermediary reveals this value. So coming to our VSS, we use replicated or additive secret sharing, where the dealer splits its secret into L parts, where here L is the size of the synchronous adversary structure, And the dealer then takes the complement of every set in the synchronous adversary structure and gives the share to all parties in each of these sharing sets. The reason why this works is that one of these sets is the actual set of corrupt parties. So the complement set has only honest parties. And the share corresponding to this complement set will not be learned by the adversary and acts like a one-time pad or mask and hides the secret. So from now on, let's refer to these complement sets as sharing sets. And the two main goals of VSS are first to ensure that the shares are uniformly distributed to all parties in each sharing set. And second, that the adversary will never learn the share corresponding to the honest sharing set. So I'll go over a synchronous VSS and we'll look at why it doesn't work in an asynchronous network. I'll then go over an asynchronous VSS and then we'll look at why it doesn't work in a synchronous network. And then we'll finally look at our network agnostic VSS. So with a synchronous VSS, I'll explain with an example so that it's a bit easier to understand. Suppose that we have 5 sharing sets and that the third sharing set is the honest sharing set. The dealer will split the secret into 5 parts and will send each share to all parties in each sharing set. The parties will then exchange these among themselves to check if they've received the same value, and they'll broadcast the results of these exchanges. The parties then construct consistency graphs where a node in the consistency graph is a party and an edge between two nodes indicates that the two parties receive the same value. So what the dealer does is it waits for a timeout, which is the time taken by these broadcasts to complete, and then it looks at which of these sharing sets have consistency graphs which form a full clique. And by a full clique, that means that the entire set of parties forms a consistency graph, which is a clique. So here, the first, third, and fifth sets are full cliques, and so the dealer will broadcast the shares for every sharing set which is not a full clique. And why does this help us? Parties agree with each other because either the set was a full clique and they already agree with each other, or they agree with each other through the broadcast. And the share corresponding to the honest sharing set will never be revealed since that sharing set will form a full clique for an honest dealer. But this does not work in an asynchronous network since we cannot rely on any timing assumptions and the dealer does not know when it's safe to broadcast these shares. So in an asynchronous network, the VSS would be like this, where the dealer will send the share, just like the synchronous case, to all parties in each sharing set. The parties will exchange these and broadcast the results of these exchanges, and parties construct consistency graphs. But now, instead of waiting for any timeout or any full clique to form, we'll wait for a partial clique to form in every single sharing set, such that these partial cliques are large enough to always contain an honest party. And this means that honest parties within each partial clique agree with each other. So what remains is for honest parties outside the partial clique to agree with honest parties inside. And to do this, we make the parties inside the clique reveal a collection of signed values from all other parties within the clique. And why does this work? This works because no corrupt party in the partial clique can reveal a value which was not held by the honest party in the partial clique due to the signature scheme. So this is great, but this does not work in a synchronous network since you may have more number of corruptions in a synchronous network, and these partial cliques may not be large enough to contain an honest party. So finally, coming to our VSS, just like the synchronous and asynchronous cases, the dealer will send the share to all parties in each sharing set. They will exchange these among each other, and they will broadcast the results. And it's kind of a mix and match of the steps from the synchronous and asynchronous cases. So the dealer will wait for a timeout, which is the time taken by these broadcasts to complete in a synchronous network. But it will not do anything yet. It will keep waiting until the consistency graph of one of these sharing sets forms a full clique. And what we show is that if any one consistency graph forms a full clique, then the consistency graph corresponding to the honest sharing set forms a partial clique, which is large enough to have an honest party even in a synchronous network. So what the dealer does is it broadcasts shares corresponding to all to all sharing sets, which are not large enough even in a synchronous network to have an honest party. And so here it will broadcast shares corresponding to 2 and 4. And with 3 and 5, we know that these partial cliques are large enough to have an honest party. So we'll use a method similar to the asynchronous case to ensure that everyone agrees on the same share. that's all for thank you.
So thanks so much. Any questions? Can I go back to your conclusion slides? Or oh, is there like any other like open problem we can work on?
Yeah. This is for the non-threshold case. So
Mhm.
the threshold adverse case is still open.
I see.
Yeah, that's the big open problem for now.
Okay, so thanks. Any more questions? Okay, if not, let's thank the speaker again. Okay, so next time we're going to have Substain Kobe talking about tumbling adaptivity in use protocols. Yeah,
Thank
please.
you for the introduction. So this is joint work with Ran Canetti, Divya Ravi, Eduardo Soria Vasquez, and Sofia Jacobo. So first, I'll be talking a little bit about the setting, and now we're in the second MPC session, so I don't need to introduce what that is. But the main difference here is that what we're thinking about now is trying to scale up these protocols to work in a massively distributed setting. So rather than performing some computation collectively across these 4 parties, we instead want to think of what if we have thousands of parties that we perhaps want to outsource some sort of computation or responsibility to, and actually still perform some sort of meaningful computation. And this can be other things than MPC. We can think of like specialized things like threshold signing and so on. So we have these thousands of parties, and we still want to perform some computation. And what does our adversary look like? So now we want to think of a quite powerful adversary. So I think the main difference here from what we've seen so far is now we'll have a lot of focus on adaptive corruptions. And that means that rather than the adversary beforehand selecting some fixed set of parties who will be our corrupted parties, we'll instead have an adversary who on the fly can decide who to corrupt. And if we think of these like massively distributed settings, kind of blockchain-like stuff, then you might imagine some sort of large-scale denial of service attack. That's still something we want to be robust against. And here, concretely, we want to think of some large corruption threshold. So here, T is some large constant fraction of our total number of parties. So think of C as a constant, and N is our total number of parties here. And of course, something we really need to focus on when we have these thousands of parties is efficiency, because our traditional MPC techniques often don't scale particularly well as we increase the number of parties. So we need to have an especial focus on improving the efficiency and doing something smarter than just applying generic MPC techniques to this kind of massively distributed setting. So the core idea in the literature on this area is trying to outsource the computation to some particular small subset of the parties. So we select out some small number of the parties who get given some special responsibility, and our hope is, and we have some sort of mechanism, some sort of role assignment mechanism for this, and we expect these parties to kind of contribute and perform their role in the computation. And then, of course, for this to give us what we need, we want to preserve some sort of relationship between our threshold in the entire population with the threshold we get in this smaller population. And this kind of approach was codified in this You Only Speak Once paper by Gentry et al., where they describe this approach where we have these parties who only speak once. And the reason we have that is because once a party speaks, it makes itself known to the adversary. So if the adversary knows that some party has some particular responsibility, then it could be adaptively targeted and corrupted. And that's what we want to avoid here. And of course, another thing we need is I need to be able to receive private inputs as a party that has some special responsibility. So I also need to be able to receive messages anonymously, and this kind of implicitly is via some sort of broadcast mechanism. So I can receive messages without the people sending to me knowing who I am, and I can pass on messages in a single action. And then if we combine this with secure erasure, so if I can erase my secret state before I speak, then that means that I can kind of pass on the torch and the responsibility before I'm able to be specifically targeted. So this is kind of the realm of protocols that we'll be looking at. So quickly, what do these synchronous YOSO protocols look like? So we have now, I'm going to introduce a term called committee. So essentially, we progressively have some subset who has a responsibility within our computation, and then they perform some local computation, send out a single message to the next committee, and we proceed like this. And then again, we need some sort of role assignment functionality to assign people to these special responsibilities, and this very quickly looks like a mess. So the way we tackle this in the literature in this paper that introduced the YOSO model, they kind of structured the approach to designing these protocols so we kind of avoid this problem of having to deal with the role assignment and everything else simultaneously. So what we do is kind of divide our world into two parts. So the first part will be something I'll be referring to as the abstract world. So here we're only thinking in terms of the committees, and here it's like abstract responsibilities within some whatever protocol we're trying to realize. And we give these some idealized communication functionality. So this could be something like a broadcast and a secure point-to-point model. And here, this allows us to more or less design MPC protocols roughly as we're used to, but with the caveat that we only have a single round of communication per party, more or less. And then we have something called the natural world, which is where we'll actually be instantiating our protocols, where we kind of map over to real-world machines. And then we need to delegate these roles to the real-world machines and actually need to realize the nomination mechanism and the communication infrastructure. And then, of course, to kind of bring this all together, we need a compiler to bring us from the abstract protocol over to our protocol in the natural world. And what does this compilation look like? So we have our abstract world protocol over here on the left, and then we want to kind of map these roles and assign them into the boxes. So here you can think of each box as a computer. And we essentially need to map our roles to real-world machines. And then, of course, we want some sort of implication that abstract security implies natural security in some meaningful way. And this is kind of what we're going to pour into with our result, trying to see like what security guarantees can you get when doing this, this transformation here. So we need to kind of use the fact that we can kind of simulate in the abstract world to help us simulate in the natural world. And of course, our paper, we're not the first people to like build this compiler because, of course, when introducing the YOSO model, Gentry et al. Needed to introduce a compiler as kind of like a feasibility result and to show that this was something that kind of you were able to bring the parts of this model together. So what they were able to do, they were able to take information theoretic YOSO protocols, which YOSO implements some functionality. And here, YOSO implementing, you can think of this as like more or less UC, but with a few wrappers and caveats. And here it's against random adaptive corruptions. And that allows you to get a compiled protocol in the role assignment hybrid model, which UC implements our secure functionality against chosen adaptive corruptions. And a key thing to spot here is that there's a difference in the nature of the corruptions we're dealing with, because these random adaptive corruptions are modeled as the adversary essentially not having control over which particular roles it gets to corrupt when it goes to perform a corruption. And that's a significant reduction in the corruption power of our adversary, which makes it much easier to realize a secure protocol. So that's something that is a desirable property. Ideally, we want to make it as easy as possible to design a nice protocol in the abstract world and still get as strong a security guarantee as possible in, sorry, in the natural world. And this is kind of what we'll be focusing on for our compiler. And there are a few caveats here. So for example, their role assignment functionality isn't realized, and they make very heavy use of non-committing encryption. And if you're familiar with non-committing encryption, you'll know that this is generally quite a heavy primitive and somewhat restrictive with respect to kind of the use cases we can get out of it. So what are some of the key ideas of this compilation approach? So one core idea is the idea of delayed honest role assignment. So here we can imagine that, okay, I don't know how well it's showing, but the boxes here on your right are red, and essentially we can imagine we have some set of currently corrupt machines. So what we want to make sure when we're kind of assigning out our roles and responsibilities is that we're not assigning any of our statically honest roles. So those are these blue circles. We don't want to assign these to any of the corrupt machines because we're not able to simulate the states of these honest machines, so we're not able to reveal them. So that's something we want to avoid. So for every role, we can kind of proportionally assign our statically corrupt roles to the currently corrupt machines. And that way we can kind of end up revealing the right proportion of roles to our adversary, but without being forced to reveal the currently honest roles. But here, for now, I'm kind of avoiding the issue of adaptivity, and that's kind of the crux of a lot of these approaches and kind of what becomes difficult. Because we can imagine over in the abstract world on your left here, we have this static adversary and we can simulate that protocol. And that means that essentially once we think of the natural adaptive world, once we've mapped over to concrete machines, then we're easily able to simulate communication that's going from honest parties to corrupt parties and from corrupt to honest. But we don't really know what messages are being sent between honest parties. And if you think of what this would look like in your typical kind of simulation, then like you would probably like replace your ciphertext with encryptions of 0 or something like that to kind of have like dummy values because you don't know what these concrete values that are being sent are. But of course, we want to kind of upgrade our security. So for the case of Gentry et al., they had random adaptive corruptions, but what we actually want to do here is something even stronger. What I'd actually like to say is, what if I can go from static security to get adaptive security? And the reason I want to do that is to kind of leverage the fact that intuitively, if the adversary doesn't know which machines have which roles, then it shouldn't have any advantage with respect to kind of targeting specific roles, which means that it can't target anyone specific. So I should be able to kind of make this static corruption, this adaptive corruption power actually map to static corruptions. But what happens if we kind of corrupt this machine which is supposed to receive a message from an honest party? Then our simulation fails and we have a problem, right? So what we can try and do to avoid this is then to, we kind of need to avoid having to open this message that is going to an honest party. So the way Gentry et al. Dealt with this was to say, okay, I have this machine being corrupted, but what if I can change the nomination? So they had this implicit assumption of, okay, I'm committing to having some nomination, but what if I can swap that party out? So this is where this random adaptive corruption comes in. So I go and make a random adaptive corruption, which means that some role which was previously honest is now corrupt. And then I kind of swap in this identity, and then I can replace this incoming message by taking my previous encryption, which had to be some like dummy value, and then replacing that with an encryption of a message in the underlying protocol, which meant that I can now take this kind of blue role, which I can't reveal, and replace it with this red role and substitute in the appropriate message that I've now learned from my adaptive corruption. But this, of course, requires non-committing encryption because I need to retroactively change the message that a certain ciphertext corresponds to. So I need to kind of equivocate for a message I didn't know, the simulator doesn't know at the time of encryption. And this, of course, is a very heavy primitive, and we'd like to kind of avoid that. So what we asked was, is there another way? So can we do this better and leverage this kind of this ability of our simulator in some sort of stronger way? So what we kind of want to, what observed is that we don't necessarily have to commit to some specific nomination. So our thought was, what if we, instead of kind of having a fixed mapping from these messages to whatever the recipient machine was, then what if I could select on the fly who the recipient was? So as my kind of protocol is running, if I could kind of choose where a message should go, so as a machine is activated, I can kind of target an honest role to that machine before it has a chance to be corrupted. And correspondingly, when machines are adaptively corrupted, I can correspondingly kind of map messages that I know from my simulator to this machine. And we can kind of proceed like this, and this way I can kind of adjust my mapping from roles to machines on the fly, and that means that I don't have to equivocate for my messages that I'm sending, but I just need to equivocate for my role assignment, which means that I can adjust my nominating committee, change how my nominating committees work. So here we have, or our role assignment works, so we combine the nominating committee's approach of Benamuda et al. With key and message non-committing encryption from AsiaCrypt last year, and then this allows our underlying protocol messages to just be in CCA encryptions. So we get a compiler which allows pretty much any YOSO protocol that implements some functionality against chosen static corruptions to be compiled to a protocol in a hybrid model where we have bulletin boards and a role assignment functionality, which UC implements the same functionality for a somewhat equivalent threshold. We also, as a to kind of complete this picture, we also realized the role assignment. Yeah, so we present a new compiler for synchronous YOSO protocols and get adaptive security from statically secure protocols. And we only need non-committing encryption for our nomination messages. Oh, sorry for the typo there. Yeah, we only need NCE for the nomination messages and none of the underlying messages. Thank you.
Any questions? If no, let's take the question offline. And thanks, speaker, again. Okay, so next talk is given by Yu Xia about broadcast optimal secure multi-party computation in the plane model. Please.
Thanks for introduction. Hi everyone, I'm Yu Xia. Today I'm going to talk about our work, which is broadcast optimal secure multi-computation in the plane model. This is a joint work with Michele Ciampi, Ivan Dangar, Divya Lavi, Luisa Senik, Lucky, and Sofia Jacobo. So previously, there are lots of amazing talk about MPC. So I hope everyone understands what is MPC. I do not repeat the definition here. So in this work, we focus on the following setting. First of all, we focus on plain model. Plain model means there's no trusted setup like a common reference string or public key infrastructure. Then we focus on malicious adversary, and we focus on the dishonest majority. The existing work shows that the optimal run complexity in this specific setting is 4 round. Namely, if you have 4 round, you can compute any efficient compute function. However, for this specific setting, we require all 4 round over broadcast channel. And it is known that broadcast is really expensive. So in order to achieve 1 round of broadcast, you can either rely on the physical or external infrastructure like blockchain, or you can run the broadcast protocol by using lots of peer-to-peer runs to achieve 1 round of broadcast. So one natural question comes to our mind is that, do we really need all 4 rounds over broadcast? Can we just replace 1 round or multiple rounds with peer-to-peer runs? And what could it be the best security guarantee we can achieve in this specific case? So in order to understand what will happen and to answer this question, we need to firstly understand what could be achievable security guarantee. Because we focus on the dishonest majority, so we know fairness is not achievable. Fairness means that if the adversary obtained the output, the honest party must also obtain the output. So usually we consider another group of security notion, which is security with different type of board. I will introduce them one by one. First of all, it's selective abort. Selective abort means that for every honest party, they could either abort or obtain the output of the function y. A stronger security guarantee is an anonymous abort. Anonymous abort means that either all honest party abort or all of them obtain the output of function y. Another stronger security guarantee is selective identifier abort, which means that for every honest party, they can either abort, identify one corrupted party, or obtain the output from the function. Note that the different honest party can identify different corrupted party. It is allowed in this specific security definition. Finally, we consider the strongest security guarantee, which is identifier abort. It means that either all honest party decide to obtain the output of function y, or all of them abort and identify the same corrupted party. So it is important to note that we cannot compare whether the anonymous board is more secure than selective identifier board or not. There are some similar research compared to us, but all of them just try to investigate the two-run cases. For two-run protocol, they require the trusted setup, and it is still remain unknown for plain model case, and we are the first work to investigate what will happen. Then as for our results, first of all, we prove if you do not have a broadcast access, you can still achieve selective board. Then if you want to achieve an anonymous board, it is required that the last run must over broadcast. As for selective identifier boards, we require that we prove that it is required the first rerun over broadcast, you can achieve selective identifier board. So finally, it is already known 4 rounds of broadcast is sufficient to achieve identifier board, and our results show that it is also necessary for you to have 4 rounds of broadcast to achieve identifier board. It shows that the upper bound matching the lower bound, and our result is really tight. Then in the remaining time, I want to talk about more details about the proof, how we prove possibility and impossibility. More specifically, I want to prove that why we cannot achieve selective identifier board if we do not have a first rerun of over broadcast. I will use one specific pattern, which is first 2 run over broadcast and later 2 run over P2P channels. So we start with the 3-party protocol, and we can extend it to n-party protocol in the end. So we assume this protocol is selective identifier board secure. And for simplicity, we consider functionality that only party out obtain the output. Then this proof consists of 3 steps. Let's go to the first step. Firstly, we want to prove that there exists an attacking scenario such that the party out must obtain the output. For the first step, the attacking scenario 1 is that the party 1 is corrupted and party 2 and party out is honest. On the first 2 broadcast round, everyone behave honestly. On the third round, party 1 will behave honestly to party out, but he will drop the message to party 2. And then in the fourth round, party 1 still behave honest to party out, but drop the message to party 2. Then in the end, party 1 and party 2 will blame each other, say, well, I do not receive any P2P message from the other party. This is attacking scenario 1. Then in attacking scenario 2, this time party 2 is corrupted, and everyone behave honestly on broadcast round. On third round, party 2 behave honestly to party out and drop the message to party 1. On fourth round, party 2 behave honestly to party out and drop the message to party 1. And in the end, party 1 and party 2 will blame each other. At this moment, party out will get confused. Why? Because in the eye of party out, scenario 1 and scenario 2 are exactly the same. It means that if party out want to abort, he will identify party 2 in scenario 2. And then he will also identify party 2 as corrupted party in scenario 1. However, in scenario 1, party 2 is honest party. So based on the SIA security definition, he cannot identify corrupt party. It means that party L must able to obtain the output. And this concludes the first step of this proof. Then it's a second step of proof. What do we want to do? We want to use attacking scenario to create a new secure protocol that is selectable secure. And it works as follows. So now we consider the new protocol and follow the same idea from the attacking scenario 1. Notice that the malicious behavior of party 1 in attacking scenario 1 now is honest party's behavior in this new protocol for party P1 new. And we do some minor modification. First of all, because only party L obtained the output, it is not necessary to have the communication on the first round between party 1 new and party 2 new. So we do not want this message. And also, only party L obtained output. So party L do not need to send the first round message to party 1 and party 2. And intuitively, this protocol should be correct and private. So the correctness comes from that because in eye of party out, party 1 and party 2 are honest. And because this is honest behavior, it means that party out must be able to obtain the output from, This is come from the proof of step 1. And the privacy hold is because now in the new protocol, we only have less message exchange. And we only want to achieve a weaker security guarantee, so it should work. And this concludes the second step of this proof. Then let's go to the final step of this proof. What do we want to do? We want to create a new adversary that can break the SA security we just proved. And this will reach to a contradiction. The core idea of step 3 is that now we want to create a new adversary that will internally run a simulator and try to extract input from honest party 1. If he succeeds, he can break the privacy requirement and reach contradiction. However, here we need to carefully handle the rewind mechanism. Note that in the play model, the only advantage the simulator has is he can rewind parties, but adversary cannot. So what we want to prove here is even if the simulator do not rewind, he still have enough information to extract input from party 1. And we need to prove it for all possible rewinding patterns. Then I will use one specific pattern as an example. So let's consider that the simulator wants to rewind the second round. Here is the simulator we want to use. This simulator is this simulator against corrupted party 1 and corrupted party out. And the simulator will have some interaction with the adversary. At some point, he said, well, I want to rewind the second round. I send a new second round message to party 1. So here we design this adversary as non-rushing in the second round, which means that party 1 can only send a new third round message back to the simulator, which contains the additional information from his input, which is helpful for simulator to extract the input for party 1. However, according to the specification of this protocol, this message does not exist. Party 1 will never send the third round message to the simulator. So it means that even if the simulator do not rewind, he still have enough information to do extraction. Then what will happen in actual attacking scenario? So in actual attacking scenario, the adversary control party 2 and party L. The party 2 internally run this specific simulator on the left-hand side, and they will communicate with each other. At some point, the simulator say, well, I want to rewind the second round. At this moment, party 2 do not need to send this message to party 1 because as I explained before, this new rewind message will not provide additional information to simulator. So even if party 2 do not send this message to party 1, simulator can still extract, have enough information to extract if the simulator only want to rewind the second round. We do similar trick for also third round and fourth round. The remaining pattern is only for the rewinding of the first round. And the intuition behind that is that it is if the simulator rewind the first round, it is similar to use start a new execution of this protocol. So by the security definition of MPC, it should be secure. And we refer to the paper for formal argument. And then up to this point, now we prove the simulator do not need to rewind the party to extract the input from party one. So the adversary can safely internally run this simulator and then do extraction from the honest party one, which will break this privacy requirement of the underlying protocol, and we reach a contradiction. And this concludes my talk. So do you have any suggestions, questions? Yeah.
Any questions? If no, let's thanks the speaker again. Thank you.
Okay, can you hear me? Okay.
Okay, so next talk is by Amit Agwa about synchronized fare exchange. Please.
Hi everyone. So I'm Amit Agarwal, and I'll be presenting the work Synchronizable Fare Exchange on behalf of Ranjit Kumar Sen, Srinivasan Raguraman, and Adam Selfon, who couldn't make it in person due to several constraints. As a brief outline of today's talk, I will first provide a brief intro to Secure MPC, as well as security model and definitions we'll be working with. I will then introduce and define the primitive synchronizable exchange, or SYX for short. I will then go over the main result of today's talk, which is that two-party primitive SYX is complete for MPC with fairness. Briefly discuss how SYX can be pre-processed. Finally, we'll look at main takeaways and related results. So let's begin. So as you have already seen, MPC involves a set of N parties, each with their private inputs, connected by means of some communication network, which we usually assume to be complete, and possessing some computational abilities, which could be local computation or access to some hybrid functionalities. These N parties wish to jointly compute some function f on their private inputs to receive outputs y1 up till yn, respectively. They do so by invoking a protocol pi, which potentially makes use of the communication network and the computational abilities. We will assume for today's talk that the protocol works in discrete synchronous rounds. So when considering secure MPC, we'll be assuming that T out of N parties are corrupt and are being controlled by an adversary A. The T parties controlled by A can deviate in some manner from the protocol pi. And the way in which they deviate depends on the kind of adversary that we are dealing with. For today's talk, you may assume that the adversary A is malicious, static, rushing, and computationally unbounded. To capture the security offered by pi, we require that the adversary, despite controlling T parties and having access to their views, cannot learn cannot learn anything more about the inputs of honest parties, apart from what is revealed from their own outputs. So MPC security is formalized using the standard real ideal simulation paradigm. In the real world, parties interact with each other and can use hybrid functionalities. In the ideal world, parties only have access to the ideal functionality, which takes in the input of all the parties, computes the output, and sends this output. And security requires the presence of an ideal world simulator, which can simulate the view of the adversary so that the real and ideal view is indistinguishable, which can be either perfect, statistical, or computational. However, the kind of security also depends on how the ideal functionality returns the output. For example, it can be guaranteed output delivery, fairness, or security with abort, as I will describe next. So the strongest flavor of security is guaranteed output delivery. Here, all parties submit their inputs to the ideal functionality, and the functionality just returns the output to all the parties. This notion of security is often hard to achieve, as an adversary can prevent the honest parties from receiving their outputs in many ways. Weaker notion is that of fairness, where all parties submit their inputs. An adversary can instruct the ideal functionality to either return the outputs to all parties or to none. This notion of security, though weaker, is also often hard to achieve. An even weaker notion is called security with abort. Here, all parties submit their inputs, and then the adversary receives its output first from the functionality, and then can instruct the functionality to give the honest parties their outputs or not. So we'll be designing our protocols in the hybrid model. In the hybrid model, we'll assume the presence of certain functionalities in the real world with certain levels of security. Examples of such hybrid functionalities include broadcast, OT, or as in this work, we'll use synchronizable exchange. Additionally, the cardinality of a primitive is defined as the number of parties involved in it, either through submitting inputs or receiving outputs. So here are some known results on known feasibility results about MPC. So from the seminal results of BGW and CCD, we know we have information theoretic secure generic MPC for T less than n over 3 with guaranteed output delivery. From the work of Fitzy et al., we have information theoretic secure generic MPC for T less than n over 2 with fairness. And from the works of GMW and follow-up works, we have computationally secure generic MPC for T less than n with security with abort. So this motivates the following question, that can we hope to get fair MPC for T less than n via some simple hybrid functionality? And by simple here, we mean low cardinality. Recall again, the cardinality means the number of parties involved in the functionality. And the reason we aim for fairness is because fairness is an important property desirable in many practical scenarios like fair coin tossing. And you might recall from Iftakh's talk yesterday that fair coin tossing is impossible to achieve in the plane model for T less than n setting, as shown by Cleve. So we will now look at a new primitive, which we call synchronizable exchange, or SYX. Looking ahead, this will serve as the simple hybrid functionality that enables fair MPC for T less than n. So before going into that, let's look at a relative primitive, which we call fair exchange, where fair exchange, so here parties, the primitive is simple. Basically, it allows all parties to fairly learn the inputs of all other parties. A fair exchange can be used to obtain fair coin toss. Parties simply locally pick their random coins and fairly exchange them and then XOR it. What is more interesting is that a fair exchange functionality can be used to construct fair MPC protocols for arbitrary functionalities. The way to do that is the following. So the parties first perform an unfair MPC with security with abort and obtain secret shares of the output of the computation. The parties then perform a fair exchange to obtain all the shares of the output and then reconstruct it. And since this exchange is fair, the output is also obtained fairly. The downside is that this functionality of fair exchange has very high cardinality, a cardinality of n, where n is the number of parties involved. This begs the question of whether there is an inherent need for a complex, that is high cardinality primitive, to obtain fair MPC protocols. Clearly, we don't need it for security with abort, as we mentioned before. And in fact, all we need is the cardinality 2 primitive of OT. Unfortunately, from the seminal result of Fitzy et al., it shows that no primitive of cardinality even as high as n-1 suffices for MPC with guaranteed output delivery. This leads to the confusing situation regarding what is needed for fairness, which is a weaker guarantee than guaranteed output delivery. This brings us to synchronizable exchange, which is a cardinality 2 primitive. It is a reactive primitive that works in two phases. The first phase is called the load phase, where each party I submits their input xi along with a tuple capital Fi of 4 functions, fload, ftrigger, phi1 and phi2. And if the tuple of both parties match, then the load phase is successful and both parties receive fload applied to their inputs. And then the functionality proceeds to the second phase. In the second phase, called the trigger phase, either party can submit a witness Wi for the predicate phi I. And if phi I applied to Wi equals 1, then the trigger phase is successful and both parties receive the witness Wi as well as the F trigger function applied to I, Wi, X1, and X2. And note that this form of two-party synchronizable exchange can be easily used to get two-party fair exchange by just loading the functionality with X1, X2, along with dummy F load 5.1, 5.2 functions that always output 1. And F trigger can simply output the private inputs X1, X2. However, it turns out that it is even stronger. So two-party synchronizable exchange will allow us to go from two-party fair exchange to multi-party fair exchange. For example, three parties with pairwise access to synchronizable exchange can perform a three-party fair exchange. And this result parallels the completeness result of OT of Joe Killian from 88. Just to answer our question, there is no inherent need for a complex high cardinality primitive to obtain fair MPC. And in fact, all we need is a cardinality 2 primitive of synchronizable exchange. So before we proceed to see a sketch of why this primitive suffice, let's recall how the definition of synchronizable exchange looks like. So here is a pictorial description. Okay, so now we'll look at how to construct fair MPC for arbitrary functionalities using synchronizable exchange. So recall that a multi-party fair exchange can be used to obtain fair MPC protocols for arbitrary functionalities. So now we will see how to construct a multi-party fair exchange using two-party synchronizable exchange primitive. So in designing a protocol for multi-party fair exchange, the n parties have some inputs S1 up till Sn and wish to exchange their inputs fairly. And we will assume that parties have pairwise access to the synchronizable exchange channel. For simplicity, we denote the pairwise functionalities by edges shown on the right side of this slide. So in our protocol, what will happen is that each party I will load the input S sub I into each of the n-1 pairwise synchronizable exchange functionalities in which it is involved. Thus, after the load phase of each SYX functionality is complete, we have the following picture. The SYX functionality between each party I and J is meant to fairly exchange the inputs Si and Sj. Then the protocol proceeds in a sequence of n rounds. In any round R less than n, any party can trigger any loaded channel with R values among S1 up till Sn. And that's essentially it. To see why this protocol works, let us consider the case of t equals 4, where party P1 is honest and party P2 through P5 are corrupt. Suppose that in round 3, party P3 triggers the SYX functionality with P1 using the inputs S2, S3, S5. At this point, both P1 and P3 will learn the inputs S1, S2, S3, S5. Then in round 4, which is the next round, P1 can trigger the SYX functionality with P4 using the inputs S1, S2, S3, and S5. And at this point, both P1 and P4 have learned all the 5 inputs, S1, S2, S3, S4, and S5. So hopefully it's clear that the protocol works, assuming the load phases of all pairwise SYX functionalities are complete. The crux of the definition of this synchronizable exchange is that it is possible to ensure that the load phases of all pairwise functionalities are indeed complete before they enter into the trigger phase. And this is the reason for calling this a synchronizable exchange. Essentially, the load phase of SYX will release a certain certificate or signature attesting to completion. And we will require that the witnesses for triggers to include all such certificates before it can be triggered. So load phases of all the n choose 2 channels must be completed before any channel can be triggered. Furthermore, since the trigger witnesses are also released on a successful trigger, if a corrupt party triggers a SYX functionality with an honest party, then the honest party gains the ability to trigger other SYX functionalities and obtain other inputs. Now note that for an adversary to obtain all inputs, it must have a corrupt party trigger SYX functionality with an honest party. And then in the very next round, the honest party will be able to obtain all the inputs. At this point, the honest party can just broadcast this input to all other honest parties so that they can obtain it. This completes the sketch of the protocol demonstrating the feasibility result. That cardinality 2 primitive, SYX, is complete for MPC for arbitrary functionalities with fairness. It turns out that this functionality can also be pre-processed. I will not go into the details, but at a very high level, instead of fairly exchanging the actual outputs, so what you do is you fairly exchange secret shares of a key which encrypts the output. I'll suggest you to look into the paper for details. So in conclusion, we have seen that cardinality 2 primitive SYX is complete for MPC for arbitrary functionalities with fairness. One question of interest is whether such a reactive primitive like SYX is an overkill. It turns out that this is not the case. From a recent result of Raghuraman et al. From Asia Crypt this year, we know that no unreactive primitive of cardinality even as high as n-1 suffices for fair coin tossing. Thus, reactive primitives are necessary for fairness. Also note that from our protocol, reactivity was precisely what was enabling the synchronization between different channels. Finally, this work leaves the open question of how one would implement this channel in practice, and turns out that this can be done using bulletin boards and trusted hardware. Details of this can again be found in a recent work by Gadam et al. Thank you.
Any questions? Okay, so let's thank the speaker again.
Thank you.
Thank you. Okay, so the last talk is by Henrik Brocher, the impossibility of surviving deletion of weakly dominated strategies in rational MPC. Please.
Yep. So thanks for a nice introduction. I'm Henrik, and the following is joint work with Johannes Blömer and Jan Bobalz on the impossibility of surviving iterated deletion of weakly dominated strategies in rational MPC. So fairly long title, and though it features rational MPC at the very end, in our results and in this talk, I will mainly focus on secret reconstruction. Namely, with this toy example, I'll start where we have 3 parties, we have a safe, and we have a rich guy which puts $60 in the safe. So just $60, not that rich. But anyway, so then he shares the pin for the safes among the 3 parties. And well, the goal of these parties is now to reconstruct the secret. Well, they want to get the money, right? In order to kind of prevent a trivial approach by kind of brute forcing the secret, we'll incur a cost of $20 per wrong try. And well, afterwards, we provide these 3 parties a communication network. So we are back to kind of a computational setting. So they share point-wise secure channels, and they have a simultaneous broadcast channel, which just means, well, at the very end of each communication round, all messages which were inserted into this channel are distributed among the parties at the same time, so we have no rushing between these parties. Okay, now consider following simple protocol for PI. Just broadcast your chair and then reconstruct the secret, right? So this works. At the very end, everyone has every chair, everyone can reconstruct the secret, everyone can open the safe and gets the money fairly. Okay, so far so good. However, well, this protocol is not fair to play, since, well, any party could choose to send essentially nothing. Well, party 3 may send nothing at all. The 2 parties on the right-hand side cannot reconstruct the secret, but party 3 can. So he gets all the money, and well, this is more rational for this party. Also, party 3 could just choose to send a wrong share, and well, this may even lead to the situation where the other parties reconstruct the wrong secret, have to pay $20, and party 3 then reconstructs the secret, gets the $60 out of the safe. Okay, so when I now say it's irrational to play, this is a very intuitive statement. However, we have to formalize this stuff, okay? And this was done by Halpern and Teague, and then refined by Gordon and Katz, Abram et al., roughly 20 years ago in the secret reconstruction game. So again, we have the setting, and at the very beginning of the game, each party chooses a strategy by themselves, and well, it's an ITM, which is just kind of well, an algorithm which can send messages over the network, and this fixes the protocol then. Afterwards, we have a trusted setup, and okay, the smileys seemingly have changed due to kind of font changes. I hope this will not continue that much. Secret is chosen. Afterwards, it is shared, and such a secret sharing scheme, in our case, has the property of T and privacy, so just threshold privacy, where T and more shares reveal the secret and less shares don't reveal the secret at all. Okay, and finally, the trusted setup ends with computing signatures on each share, such that kind of we can overcome the second part of the second attack from the toy example before, and then these are distributed among the parties. Now, in order to facilitate notation, I will just put boxes around a share when it's signed, which kind of visualizes some stuff later on. Okay, now the parties run their protocol, and after the execution, each MI outputs a guess on the secret. Well, this is then called in game theory usually an outcome of some game, where kind of each party's output is kind of put into a tuple of guesses in this case. Lastly, now we can formalize what utility or rationality means, namely each party has a utility function UI, which maps such outcomes to some utility. In the previous example, it would have been, for example, $60 for party 3 when he were the only one to learn the secret, right? And what was then assumed was that in many secret reconstruction protocols and also in MPC, we usually have two properties in such utility functions. Namely, we have the desire to output the correct secret or the correct result of a computation. This was the case in our toy example, right? So we could either pay $20 if we output the wrong secret or get $20 if it's correct. Also, we usually had for exclusivity in such computations, well, this was the case for party 3 in the toy example as well, where he got $60 instead of $20 when all the other parties got the secret. Okay, now what was considered in the literature is, well, how can we design secret reconstruction protocols which reconstruct the secret at the very end and which are rational to follow, right? In the previous example, we had a protocol which was not rational to follow. And it was indeed not rational to follow in the sense of a Nash equilibrium. So this is the most standard notion from game theory, I'd say. And well, it just means no party can exchange its strategy from a prescribed protocol in order to substantially improve the utility throughout the protocol line. Right? In the toy example, it was possible for party 3 to exchange its strategy and thereby increase its utility. Okay, and well, the state of the art back then was, well, such protocols as the simple protocol in the very beginning fail since, well, in the last round of the protocol, a rational party will not send anything meaningful to the parties. Right? And they overcame this problem by randomizing essentially the round in which true shares of the secrets are used. And well, so this then led to the design of Nash equilibrium protocols, which especially holds for this NN private setting. It's especially for this toy example, for example. However, the authors of the papers above also headed for a stronger rationality notion. Since, well, Nash equilibrium, they meant, and also we think, is not sufficient in all scenarios. And in particular, they wanted to get the notion of surviving iterate deletion of weakly dominated strategies, or for short, IDOUBTs. Okay, so what's weak domination? A strategy is weakly dominated if there is another strategy which is never worse against any opponent strategy, but sometimes it's better, right? And intuitively, if we think we have a protocol and we know our strategy is weakly dominated by another strategy, why shouldn't we change to this weakly dominated strategy? Well, and that's the essential meaning behind these lot of words, so behind this IDOUBTs notion. No protocol prescription or no strategy from our protocol must be weakly dominated. Okay, what we now have shown is that essentially any protocol in the most reasonable settings have at least one protocol prescription or one strategy included, which is weakly dominated. And this was different from what was claimed back then and was then refined later on. So that's basically our results. And the intuition behind this is really, really simple. On the right-hand side, consider the concrete protocol from before, where we have some concrete strategy M3. We can just extend it by a check whether the other parties send us their shares, so their true initial signed shares, together with some leaked message or something. So in the original protocol description, such a message is simply discarded. In our description, it is obviously not discarded, and thereby in the improvement, we get all the money from the safe. Well, and this is not worse than the original protocol if we assume we have a sufficient authentication on the shares, so we can really check whether we got the initial input shares. So in this case, well, the if condition will be false unless there was a forgery, which only happens with negligible probability, sorry. And thus we get the same utility as M3. And this now generalizes to arbitrary protocols. So we have really black box protocols. So the strategy which we consider as some code, then the first communication round ends, then we have another code. Well, we can improve it by the same check as before. No, in fact, we can't, since this check could also be included in this black box strategy, right? So then we kind of change our check to something where we flip the last bit of the message and check then whether the resulting message ends in some correct signed share. Well, this check could also be included in the black box. And well, what we essentially have proven is that for some case, such a check cannot be included in the protocol, right? So we use the non-uniform setting for this. This can be overcome in a more kind of gray box fashion. However, well, that's kind of the main result for just single party deviations. And yeah, so I think in order to not delay the break too much, I'll already get to my contributions or our contributions. Namely, we generalized these results in the sense that we also looked on what happens if rational parties group together and kind of share their utilities. Well, there we got some results. So the first row of this table just means, okay, this is just a generalization of the example we have seen before. If the shares are signed or authenticated by something which we can locally check, then the previous result applies and the resulting protocols are weakly dominated by something. The second row just applies to kind of more implicit forms of authentication, which are part or which are kind of attributed to Reed-Solomon codes. And the last row is kind of, well, if the parties have the possibility to change their shares in order to change the reconstructed secret, but by kind of getting the reconstructed secret can then get the original secret back, then we cannot have a Nash equilibrium at the same time as a not weakly dominated protocol. So that's kind of, these are the main results from our paper. And well, for the future, it's open whether we can show something for coalitions which are non-majority in the last setting. And also, how should we proceed with weak domination, right? So what we have shown is that, well, it's rarely achievable. And back then, it was also shown that there are problems with this notion. However, we think weak domination has some nice features. So look at this protocol. It features a very disturbing if check, which is kind of really bad. But weak domination is really good at pointing out such irrational checks in protocols or something like that. Other notions which also have been put forward in the past don't find such checks. And even though this seems like a toy example, we think some form of rationality notion should kind of rule out such meaningless protocols, we think. And therefore, we are currently looking into new notions which keep the essence of weak domination, but kind of formalize it in a different way. And one such notion was proposed by Hillas and Summit 3 years ago, and is named iterated deletion of weak flaws. And well, now that really concludes my talk. And yeah, thanks for your attention.
Any questions before the break? Oh,
Um, so I would say that like the examples of weak domination in your case like can be considered contrived in the sense that the parties deviate from the protocol. And do you have any results regarding a weaker like we could consider a weaker notion that we can consider weak domination, but assuming that the messages adhere to the protocol, the parties might send like invalid inputs like for what they have, but they still have to be syntactically correct, and this removes those example of yours. And do you have any results for that?
Yeah. So indeed, this is something which we kind of considered as well. It's kind of hard to formalize what you're kind of requiring here, right? So what are kind of syntactically right messages in a protocol, and why should we restrict the rational parties from picking such strategies when choosing their strategies? Since, well, this whole setting, when we consider each agent or each party of this protocol as an individual rational agent, well, they have the whole possibility set of possibility space of all the ITMs, right? Does this answer?
So this could be like sensible in a setting where we would assume that the parties did like the point is that if the message is not syntactically correct, then if the other party would do anything, then the parties need to collude, and like collusion prevention is another kind of worms, but in a collusion-free setting, this could be like reasonable.
Yeah. So I think you already mentioned the thing here. So on the one hand side, it would be possible to kind of include your true share in some meaningful message, so kind of in a subversion way. And well, that's kind of also problematic already. So, and therefore we kind of did not took this path by restricting these messages. And also, like I said, I think it's not meaningful for the model to kind of discard some of the strategies already at the very beginning of the game. But we can take this discussion offline, I guess, maybe. But thanks, that's a nice question.
great. Let's thank all the speakers from this section again. And yeah, please enjoy the coffee break.
in my slides.
You did not.
I could try to get them off.
So we have on the hub right here. So if it's possible,
I just saw the 11:30.
okay. It's confused on some. Yesterday, it's 11:29.
Right, yeah.
But it's also the time. Yeah, look, you're talking to the UN or something.
I know. It's quite the room.
It's actually it's nice. Yes. Do we need to? Do you have research to do it from here?
My laptop is that way.
What's better?
I think we should use our device because we're going online.
Okay.
There's
Oh, I
some
see.
people
Is it a
online.
Can I email it to
Yes, sure, sure. Yes.
Yeah, but then I have to get my phone
I've
on
got
the
a
internet.
flash drive if it's
Oh,
possible.
I can do that.
Okay.
Your PhD is on anonymous credential, right? Good. I'm not ready for the answer. You know that's not for us. The whole thing is not for us. It's for the new generation. That's
Funny that there's a whole generation.
no, I don't know anybody. I know only the old people.
That's what.
So anyway, but many compliments from Joel because he's also into cooking. He's, I want to say obsessive about it. And as I mentioned, yeah, they did a great job there.
Yeah, it was exciting that they're using that inspiration.
It's very nice to see that the stuff is deployed. But now we know there's a catch. Access pattern.
Oh yeah, there's a lot of things that could be improved, but
I'm
sort of
going
trade-offs.
to mention that as well.
Fair enough.
Just
And then you decide when we start. So we reach a decision where I'm the session chef. I have never in my life seen such a complicated
We can start? Hello, everybody. Welcome to the Test of Time award session. As the awardee, we have Melissa Chase, which we're very happy that she made it in spite of all the challenges. So thank you, Melissa. Melissa is a principal researcher at Microsoft, working in the cryptography, security, and privacy group. She receives the award, the TCC Test of Time Award 2023, for her paper Multi-Authority Attribute-Based Encryption, for the first attribute-based encryption scheme in which no small subset of authorities can compromise user privacy, inspiring further work in decentralized functional encryption. Let's congratulate Melissa. Come here. I want to add just a few words about the award, about Melissa's work. So Melissa wrote this work when she was a PhD student. As you notice, it's a single author paper, which adds to the how nice it is, this award. She started off as a theoretician working on anonymous credentials, and actually did practical stuff that was very impactful in that direction, not in her capacity as a Microsoft employee. She actually influenced directly the Signal protocol for group messaging, using anonymous credential to manage identities of users in group across a long period of time. We just talked about it. We said that it's not a perfect solution theoretically, but it's good enough for practice. In particular, it discloses the access pattern of users to their keys. So anyway, it should be inspiration for all of you to do also work that have a practical impact. That's all I wanted to say about the subject. So Melissa, the stage is yours.
Does that work? Cool. So I thought today, maybe instead of talking about that one work, I'd try to give a bit of a history of attribute-based encryption. I'll just say this is an area that I've sort of jumped in and out of over the years, so there are other folks in here who've done a lot more of the work. I'll try to be good about citing people. But I think it's a really cool area, and it's also had some really exciting developments lately. At the end, I'll talk about how it's now being used on a global scale, which I think is super cool. Yeah, so I'll just start at the beginning of history and sort of step through and talk about some of the key results. There's better? Okay, talk about some of the key results. I'll just say there's a lot of work out there, a lot of cool work, and if I skip your favorite result, it's my omission and not that your result is not cool, or that whatever result is not cool. Right, so starting way back in time. So back in time, we had public key encryption. We all know this very well. We have users, they have public keys and secret keys. And when you want to encrypt, you figure out who you want to encrypt to. You look in some kind of directory, you find their public key, and you use that public key to encrypt. So that was sort of, actually still sort of how the world works, but there was this cool idea that Ali Shamir came up with in 1984, which is called identity-based encryption. And the idea there is that, wouldn't it be nice if instead of having to look up the public key for a particular person, we could just use their identity to encrypt to them? So how does that in practice work? So they need to be able to decrypt based on who they are. So they're going to go to, say Alice will go to some key server and say, I'm Alice, prove her identity, and get back a key, and so on for everybody else. So Bob gets a Bob key, and Carol gets a Carol key. And now when the encryptor wants to encrypt, they just need to know they're encrypting for Alice, and then they can encrypt the message. And they need, I guess, the public key of the server, which I don't have on here. So this was an idea back in 1984. It was a cool idea. We didn't know how to do it, but Bonet and Franklin in 2001 showed that we can do this from bilinear pairings. And there's also a cool construction by Cox from quadratic residuosity. So that was great. Now we can do away with public keys and encrypt directly to identities. But there was another interesting idea that came up. Sahai and Waters in 2005 said, well, what if the encryptor and decryptor addresses don't match exactly? Like, can we add a little fuzziness in there? Maybe there's some threshold and they just need to be close. And then they took it a step farther and said, well, now that we're allowing some thresholding, we're allowing some fuzziness, what if we think about it not as one identity string, but as a set of attributes? And that sort of started the whole direction of attribute-based encryption. So now we say Alice has some attributes. I say she's a Brown affiliate, she's 25 years old, and she gets back a key for that. And then Bob has his attributes, and he gets back a key that corresponds to those, and Carol, so on. And now the encryptor can encrypt and say, I'd like to encrypt this to a Brown affiliate. You can see how old these slides are because they're still talking about Brown, which is where I did my PhD. But so then, now we can say maybe Alice has something more complicated. Maybe she's got a Brown ID, she's income in a certain range, age a certain range, and so on. And now the encryptor can come along and say, well, I want not just this one fixed thing, but I want to be able to say, I want this to be decryptable by anyone who has two of these three attributes, a Brown ID, income in a certain range, and age in a certain range. Oops. So this is, again, the same picture, just I'm going to use a little bit more of the pictures I'm going to use for the rest of the slides. So Alice says she's between 25 and 30, and she has a Brown ID and gets back keys for those. Bob has income in a certain range and has a Brown ID and gets back keys, and Carol similarly. And now when the encryptor says, I want to encrypt to anybody who has two of these three properties, then Alice should be able to decrypt because she has a Brown ID and she's between 25 and 30. Bob should be able to decrypt because he has a Brown ID and income high enough, but Carol can't decrypt. So that's nice. And just to say what makes this sort of interesting to construct is that we don't want collusion. So if we have Bob who's, say between 30 and 40 and has a high income, we have Alice who has a Brown ID, but she's a 5-year-old. And then we want to encrypt to somebody who's between 25 and 30 and has a high income. And has a Brown ID, and so two of those three. Now, if you notice, those two people should not together. They could satisfy two of the three because Bob has a high income and Carol has a Brown ID, but by themselves, neither of them has enough attributes, so they shouldn't be able to decrypt. So the idea is to make sure that they can't combine their secret keys somehow and decrypt the message, and that's what makes constructing these things slightly non-trivial. So I'm going to give sort of a rough outline of how this construction works. It's actually really fairly simple, certainly compared to modern AB constructions, but I think it gives some intuition for how these things work. And it's a nice history lesson. So okay, the key tool we use is polynomial secret sharing, so that's pretty easy. And then we're going to use it sort of in the exponent of a multiplicative group. So say we have G, which is an element of the group, and then the nice thing is that if I give you G to the P1 and G to the P2 and so on, you can reconstruct in the exponent and get G to the P0. And obviously so on if it's multiplied by X, and that's sort of what we're going to use. Okay, so what does this look like? So basically, if Alice has two attributes, she's going to get sort of two key components. And if the ciphertext is saying you need two 2 of 3 attributes, and there are going to be sort of 3 components in the ciphertext. And just for now, say that the Alice matches the first 2 of those components. So that I'm keying the attributes by color. So there's the red attribute and the yellow attribute. And then we're going to basically lock up blind the message with something. So the public key is going to be G to the Y. A secret key is Y. Just say the threshold is fixed at 2. Then we pick a polynomial for this user, say, and set where the 0 of the polynomial is the secret key, and it'll have degree 1. And now we're essentially going to somehow give you some red component that's tied to P, so it'll be like evaluation of P, somehow have the evaluation of P at 1. And then the yellow component, say the evaluation of P at 2 rather. And then the ciphertext is somehow going to embed some randomness X. I'll talk about how in a minute. And then we'll take G to the YX, so that's the public key to this randomness X, and use that to blind the message. And then we're going to try to set it up so that if you put together the red key component and the red ciphertext component, then you get G to the P1 of X, P1 times X, P of 1 times X. If you get the yellow one, you get G to the P of 2 times X. And then even if we only have, if you had the blue one, you would get G to the P of 3 of X, P of 3 times X. And any 2 of those is enough to reconstruct the 0 of the polynomial because it's degree 1. So now we can get back G to the P0 X, and that's the thing we use to blind our message, so we can decrypt. And the key part here is that we wanted to prevent collusion, and the nice way you do this is just to pick different random polynomials. So now, let's walk through again, but if we have Carol who has this red attribute, Bob has the yellow attribute and some other green attribute, then we're going to use different polynomials. And so Carol will get G to the P of 1x, and Bob will get G to the Q of 2x, and those put together don't give you anything useful. Okay, so that's sort of good, but how do we actually embed these values? Obviously, if I just give you a polynomial, points on a polynomial, then you'll be able to solve some linear equations. And also, I can't just give you X in the clear. So how do we do this? So we're going to use bilinear maps, basically because we have a secret we need to hide on the key side and on the ciphertext side, and we want to put them together without letting you learn discrete logs. So bilinear maps, probably you've seen these by now, but we have groups. Right now I'm presenting it in the symmetric setting. So we have groups G1 and GT, and then there's a function that maps G1 and G1 to GT. And it has this nice property that you take E of G to the A and G to the B, you get this element, basically E of GG to the AB. So it sort of lets you solve this DDH in the exponent, or in the, yeah, lets you solve DDH, but it moves you to this other group is the weird thing. And just to say, this is not really how things are done anymore. We use different groups and somewhat different assumptions, but this is a nice simple picture. Okay. Right, so how does this fit in? So the idea is going to be, the thing you get out is going to be in this target group, the big G. And then the public key will now include, as well as the G to the Y, it'll have 3 elements, 1 for each attribute. So G to the T1, G to the T2, G to the T3. These little t's are just random exponents. And then the ciphertext can now just take those things from the public key and raise them to the randomness. And then in the key, we'll put G to the P of 1 over T1. So over that secret T that we picked for the first attribute, and so on. And now by the bilinearity property, you can put them together. And so that it combines, so that was the bilinear mapping. So now we get everything multiplied together in the exponent, and you cancel the thing out. You get G to the P1 of X, which is just what we want. So that's at very high level, the construction. Talk a little bit about the security we want. So this is the security we would really like, is to say that we have an adversary, it plays this game. In the game, the first step, we run a setup. So this is sort of what the key generation key server would do. So which generates a public key and a secret key, master public key, master secret key. Then the adversary can get that public key and then request keys for different attributes. And then we run the key gen on the back end using the master secret key and the attributes and get back a key. And then at some point, he can request a challenge ciphertext, so give 2 messages and a set of attributes. And of course, these attributes sort of have to not be satisfied by the attributes you gave out in the key. So in the case of threshold, that means these need to be different enough. They can't have an overlap that's more than the threshold. And then we get back a ciphertext that encrypts a random message. And then you can request more keys, again with the same constraint, and in the end you have to guess what the message is. So this is a nice definition. I think it's pretty natural, but it is not actually what at least most of the initial works could satisfy. So most of the initial works worked in this area model called selective security, where first the adversary says, these are the attributes that I'm going to use in my ciphertext. And then we do all the things on the right-hand side. So then we generate a public key, then we do the key and so on. And then in the challenge ciphertext step, we just use those attributes that the adversary gave at the beginning. And why this is important is because it means in our reduction, we can sort of program in those challenge attributes. So we'll set up the parameters so that those attributes are things that we can give away, and all the other attributes sort of we can't. Or sorry, I should say, something like that. And that's sort of what has made it really hard to get around, because it really involves this programming of the attributes that are fixed at the beginning. And I'll talk later about sort of how we get around that. So we had attribute-based encryption. It was sort of I think has spawned a big field, and actually a huge number of citations. If you search on Google Scholar for attribute-based encryption, it comes up with really large numbers up on the scale of like multi-party computation. And I think the reason why it's very easy to understand problem, and it also sort of comes with a nice application story. So you can say, oh, I'd like to store my files encrypted, but I want to be able to control who can access them. And I think that makes it sort of easier to grasp and more fun to play with. And then the other thing is that there's a whole bunch of features that you could imagine wanting because we have such a nice natural application. I think those together have spawned a huge field of work. So I'll just talk through a little bit of them. Or I'll talk through some of the properties that have come up sort of in the order that they happen. So I guess one of the first things that happened was people said, okay, thresholds are nice, but maybe we can do more. So what if the first suggestion was key policy. So the ciphertext will have a list of attributes, and then your key will say, these are the types of attributes you can decrypt. So some Boolean formula on Boolean formula on the attribute. So you'd say, if it says it's low security or it's high security and it's in my field or something like that, then I should be able to decrypt. The next thing that came up was actually really even more natural. I think it's just ciphertext policy. It was a little harder to construct, but so that says that the policies should be on the ciphertext side, and the keys just correspond to attributes. So maybe I get a key saying that I'm a doctor, and I work at another attribute saying that I work at this hospital, and another attribute saying that I don't know, I'm this age or something like that, or I've been working there for this long. And then the ciphertext will give exactly a formula on those attributes. So it would say either a nurse at this hospital or any doctor, something like that. So that sort of opens up a lot more options in terms of applications, because it's often easier to assign attributes ahead of time. And then when you get the message that you want to encrypt, now you know exactly who you want it to, what restrictions you want to place on who can access it. So another cool thing that happened was support for negation. So we would like to be able to say, like, anybody can decrypt except somebody in this department, or except somebody who has a restricted permissions or something like that, except a guest, for example. Another thing that I think often gets swept under the rug, but I think is very cool, is and works really well with the negation, is looking at attributes not as, do you have the attribute nurse, but as a pair of like a label and a value. So role equals nurse, hospital equals B. And this is nice in conjunction with the negation, because now we can say, like, if you have a role that is not nurse, then you should be able to decrypt. But on the other hand, yeah, it makes it, if you look into it, it's sort of hard to define that. knots in a nice natural way if you don't have these sort of attribute value pairs. I guess another cool idea was hiding the attributes. So in the default scheme, the attributes on the ciphertext are visible to everybody, and also on the secret key comes along with a list of the attributes. And in fact, you need to know those attributes in order to decrypt. For example, in the threshold thing I gave, you wanted to know which attribute to pair up with which part of the key, which attribute in the ciphertext to put together with which part of the key. So these attribute hiding schemes try to hide either on the key side or on the ciphertext side. And I guess the last thing I was going to mention sort of in this period is multi-authority schemes, and this is the work that I'm going to talk about. This work from 2007. And I'll also sort of mix in some nice ideas from our 2009 paper that improved this. Okay, so the idea is we would like to have multi-authority AVs. So in general, like when you think about attributes, it's not necessarily the case that one entity controls all the attributes of your identity. So for example, we might have a university, a credit bureau, a DMV, and they might all control different things. So maybe Alice goes to the university to get a university ID card, but she would go to the DMV to get something proving her age. So now, now what we'd really like is to be able to have the same sort of thing we had before, where we can say, I want to have some threshold, but have these attributes split over to different authorities. And what we did in these early schemes, because it was easier, was to say that we're actually going to say I want a threshold under each of the three authorities. So these are the fixed set of authorities, and I want to say two of these three attributes, which are given out by, I don't know, by the Brown server, and one attribute by the credit bureau, and one attribute by the Rhode Island DMV. Something like that. And so how does this work? So we're going to use colors again. So again, Alice is going to go to the Brown server, and she'll get some key corresponding to the fact that she is a Brown student and is in this age range. She'll go to the credit bureau and get a key corresponding to the fact that she has good credit. She'll go to the DMV and get a key saying that has a Rhode Island identity card or something like that, and so on. And now she should be able to decrypt if she has two of these, two things from the Brown server and one of these things from the green server, and one of these two things from the purple server. And again, we don't want collusion. So if Alice has some of the things, and Bob has one of the other things, so Bob satisfies the purple server part and Alice satisfies the red and green server parts, that should not be good enough. They shouldn't be able to combine and decrypt. So that's great. So why can't we just reuse the single authority techniques? So we could think about, we'll just take the master secret key and secret share it across these three authorities. And now they'll just each use that as their master secret key, and then everything will add back up. So we can give out the keys. Alice will get a polynomial from the first authority, and then a different polynomial for the second authority. So the first polynomial will have 0 y to the r, or y sub r. The second polynomial will have 0 y sub g. And then Bob maybe gets something with 0 y sub p, and then maybe they put it together. And this is a bit of a problem because now potentially they can put together all these three parts, even though Alice only has satisfying things from the first two authorities and Bob has something from the third authority. And so what do you get? I mean, there's sort of an underlying impossibility result, which is that if you look at the two scenarios, one where Alice has all the satisfying attributes, and the other where Alice has only the right attributes from the red and green server, and Bob has the right attribute from the purple server, there's sort of no way for the servers to tell the difference unless we add some identity. So we have to add this extra step that says that the user has to have a unique global identifier. It needs to be sort of unforgeable and that nobody else can claim their identifier, and all the authorities should be able to verify that it's actually theirs. So this could be like a name or an email or some other sort of unique identifier for a user. So now Alice goes to the first authority and says, these are my attributes and this is my name. And the authority checks, yes, Alice has these attributes, and gives back something for that. And she is actually Alice. And the same with the second server. And now Bob will get his own key, but it will be tied to his identity, Bob. And so that now we want to say we shouldn't be able to combine the Alice keys and the Bob keys. And so, okay, how can we do this? So, so first attempt, or I mean, not really first attempt, but that was our first attempt. And now the one idea for how to use the GID is, well, what's, instead of using a fixed Y, let's use a different Y for every user. So Alice will go to the first server and present her attributes, say she's Alice, and then the server will compute a special pseudo-random function on her ID and use that as the Y from that server. And then she'll go to the second server, which will compute a Y based on her ID again, and the same with the third server. And now the thing is, Bob would have different Ys, and so that means that he would be able to combine his values with Alice. They'll come out to, when she combines her values, she'll get these things tied to Alice, and Bob would get something different, so they're not interchangeable anymore. So that's great, but the problem is we need to encrypt, and somehow we need to remove this blinding factor due to the YX. So now we need to make sure that this Y sub R, Y sub G, and Y sub P all add to the same fixed Y. And for that, we sort of need an extra tool. Basically, what we're going to set up is that each server is going to have a seed. I wanted a picture there, but it's okay. So they'll be able to compute this F sub I, so F with their seed, so of an input X. So get the red, the colors are really short, but the red F of X, the green F of X, and the purple F of X. And we want that they always all sum to the same value. That's sort of the extra thing that we want. And then we want that each of those individual values still looks pseudo-random, even given all the other seeds. And it turns out you can construct this sort of from any PRF. There's a cool trick where you basically make sure that so you have every pair of servers shares a pairwise seed, and then you make sure that when they add up, they all, so each server is in charge of, evaluates the function using all of the pairwise seeds that it has, so the seed that it shares with every one of the other users, and they either add or subtract to make sure that they all cancel out at the end. And then they can each add that gives you something where they always add to 0, and if you want them to always add to a fixed value, you have them also add one fixed share of a fixed value. So they each have a share of the fixed value. And so we just plug that right in, and it actually works really nicely. So now these servers there's a setup phase where they all have to have sort of coordinated seeds, and because we need these sort of pairwise shared seeds. That's sort of unfortunate. It gets cleaned up by other people in later work, which I'll talk about later. But given that, we can construct this thing in just exactly as before, except that now we have these special PRFs so that our Y values just always add up to Y. So if they're all from the same user, they always add up to Y. Okay. So that was great, and that's sort of where we were as of 2009, and then 2010 came along, and all of a sudden we could do full security, which was very exciting. So just to briefly refresh full security, the idea is that instead of selective security, where we have to commit to the ciphertext attributes that we're going to use at the very beginning before the public key is generated, now we're going to say that you don't have to give those attributes until you request the challenge ciphertext, which removes our ability to program things in, but it's still doable. So the sort of key thing that we needed for this was the dual system technique by Waters from 2009. And so I think there's actually 2 different groups that solve this problem simultaneously, but nice solutions. Yeah, let's see. So I'll just say many of the first constructions are based on composite order groups. The constructions and analysis at the beginning were fairly complex, and that's something that's been worked on a while. So I wanted to give just sort of a rough idea of what the proof approach is like. This is not exactly what it's like. I'm sort of squishing a bunch of details under the rug, but it's something that gets used in a lot of the subsequent work, and I think it's sort of cool ideas. And I'm going to use notation from from 2 other works, We and Atrepidon, because it's cleaner, and I'll talk a little bit more about those later. Okay, so very roughly, the idea is we're going to use composite order groups, where you have a group that has your pairing group actually has 2 subgroups in it. So say a G1 subgroup and a G2 subgroup. So G1 and G2 are going to be the generators for the subgroup. Excuse me. And then, so just as a way of sort of abstracting what the picture looks like, there's something that'll be in the target group. So that's this GT on the left, that's now the target group value. It used to be capital G, sorry for the change in notation. And then that raised to the alpha S. Alpha is that secret, it used to be Y, now it's alpha. And then S is what used to be X, so it's the randomness for the ciphertext. So you're gonna hash that thing and multiply it by M. The hashing was sort of implicit in the previous schemes. Here it needs to be explicit because we're gonna need the fact that you sort of mix up the randomness a little bit more. So these won't be completely random, but they'll be random enough that once you hash them with, for example, a pairwise independent hash, it blinds the message. And then the idea is we're gonna look at what happens, those values I gave out in the initial scheme, it was something like TI to the TI times X, and in the exponent is like G to the TI times X. So we'll just encode all that as saying there's some function, inc, that takes some public parameters, so those would be like the TIs as the Ws, and then the description of the attributes. And then on the key side, we'll also have the sort of a key function that takes the description of the attributes in the key, or policy in the key, or whatever it is, and the public parameters. And then that's going to be somehow added. I'm just saying adding for now. Really, there's something more complicated there, but with the alpha, which is this master secret. Okay, so that's sort of the setup. That's what your scheme looks like. That's how it works. And I'm actually going to start out where the ciphertext has both a G1 component and a G2 component. And just, we'll go with that. I'm again sweeping a lot of details under the rug. But so the idea is we're going to use, let's see. Okay, so first, just to make things nicer, ignore the G's and just look at what happens in the exponent, because otherwise it gets too messy to read. Okay, so the first thing I'm going to do is I'm going to use the subgroup decision assumption to add a G2 component in the key. So that's just saying now I can duplicate what's happening in the key. Now I have a G1 component, G2 component. So it used to be, say here I had H1, but H1 or G1 to the alpha plus our key function, and now it's going to be H1 times H2 to all that stuff. And then the next step is going to be to say, okay, now that we have separated the G1 component and the G2 component, so the G1 component, basically what you're going to get, there's some exponent that's mod n, which is n is your RSA modulus. And then you're going to take, then the G1 component, you'll get basically that exponent mod P1, and the G2 component, you'll get that exponent mod P2. And what that means is that those two things are completely independent. So we can actually write it as S and S hat, and then W and W hat, alpha and alpha hat, R and R hat. So they're sort of completely independent values. And this is just like information theoretic. It's exactly identical. So it's basically saying I could choose the thing mod P and mod Q and then put it together, or I could, just choose the whole thing mod N and then, put it in the exponent instead. So now once we have it separate, now these are completely independent exponents. Now we can look at this sort of right-hand side, and there's going to be some trick, and this is sort of the subtle part in these proofs, is we're going to try to argue that if the key attributes don't satisfy the policy in the ciphertext, that you can't tell if I add an extra. So if I give you one key and one ciphertext, and if the key attributes don't satisfy the policy in the ciphertext, then you can put this extra beta in there and nobody will be able to tell the difference. So basically that you can't tell if the key has the same master secret as is in the ciphertext. And that's sort of, there's different ways of proving that, and that's sort of one of the technical challenges in proving these schemes. And then now that we have that, now we can go and sort of step back and say, okay, now maybe instead we'll go back to generating one alpha and putting it in the exponent of, say H1, H2 to the alpha and so on. But we still have this leftover beta. And so now when we clean everything up, we're sort of left with a beta on the outside. So now if we do this with each key, what we're doing is sort of adding a beta in each key. And then at the end, what you get is that on the key side, everything is alpha plus, beta in the B2 in the G2 component. But on the other side, everything is alpha. And so we can say that if your hash function is sort of good enough at spreading things around, then you can't tell. Given this alpha plus beta in the G2 component, that's the hash of the original alpha, the G to the original alpha, it looks uniformly random. And that's sort of a statistical argument if H is a pairwise independent hash. So that's sort of the, I guess, the key idea of this full security. And I'll talk a little bit more about the abstractions to make this cleaner. Actually, it's much more complicated in the real proofs because to make the subgroup decision go through, you have to add some more steps. But this is, I think, sort of what's going on under the hood somewhere. Yeah, and I think so. The most there's a bunch of interesting steps, but one of the interesting steps is where you add this beta, and we'll come back to that. Okay, so then going back to sort of our timeline. So in the next 5 years, we added a whole bunch more features. So partly having this new tool to play with helped, and partly just more progress. So one nice thing is compact ciphertext. You can actually make it so that the ciphertext doesn't scale with the number of attributes. So you saw before in the ciphertext, there was like a T1 to the X, T2 to the X, T3 to the X. So the more attributes you add in your policy, the longer it gets. So you can actually squish that down. Another thing was, you saw that the parameters scaled with the number of attributes. So the public key had a G to the T1, G to the T2, and so on. So we can, you can get rid of that. Another cool thing was decentralized ABE, which I'll talk about in a minute. That's essentially the improved version of multi-authority ABE. And I'm not going to talk too much about it, but there was also some really nice work on lattice-based ABE. It took a lot longer to come up with the first solution because it's tricky. But the cool thing is now you can do things like ABE for circuits. And there's been a lot of progress on that front. Okay, so I'm going to talk more about the decentralized ABE because it's an improvement of this multi-authority ABE. So the idea there is again, we're going to have an authority who controls an attribute. And here, for simplicity, since it's so easy, we're going to say each authority is going to control a different attribute. So one authority per attribute. You could have one authority be more than one, but it doesn't change the scheme at all. So they have an attribute they're going to control. They publish a public key for that attribute, and they issue decryption keys. So anybody who comes along shows they own that attribute, and they have a particular ID, and then they give a decryption key for that attribute tied to that ID. And now anybody can come along and look at the subset of authorities that are out there, pick their whatever attributes they want in their policy, and put all those public keys together and encrypt their ciphertext. So there's no coordination required to set up the authorities, and you don't have to have a fixed set. You can just, everybody can come and publish their own public key. And then anybody who has gotten decryption keys from an appropriate number of authorities can do. And what we really want to get is we don't want to have to trust all the authorities who are out there in the system. So we want to be able to say this is secure even when some of the authorities are encrypted. So the initial constructions had a number of restrictions, and there's selective security, and I think restrictions on how the authorities could be corrupted. But this has made a lot of progress, and as I understand it, at least this recent work, and I think Eurocrypt this year, gets sort of the optimal security model. So it's fully secure. You don't have to do this committing to the ciphertext attributes beforehand, and it's secure against adaptive corruption, so you can corrupt authorities as you go. So I think this is the modern multi-authority ABE, and this is what everybody should be looking at and reading now. But yeah, I'd say it's come a long way, and it sort of solves the problem nicely. Okay, so going back to sort of timeline, I think the next really cool thing that happened was this sort of simplifying the constructions and analysis. So as I mentioned, sort of the initial fully secure constructions were pretty complex. The analysis was sort of long and complicated, and if you wanted to use dual systems for something new, you had to sort of do all that over again. And it sort of makes a very high barrier to entry, and it means a lot of papers with a lot of really long proofs to generate and check. So I think one of the cool things was to say, well, why don't we see if we can sort of do all that work once and then just do the easy part multiple times. So I think that was sort of the motivation behind these two works, from pair encodings and predicate encodings. So they're the ones who introduced this sort of model of looking at just like what happens in the exponent is just an encoding using the parameters and inputs, and also saying that there's sort of this key step of adding this beta if the keys if the key doesn't satisfy the ciphertext. And so they sort of formalize sort of what you need from the encodings to make it so you can actually get your message when you want it, when you should be able to decrypt, and also what you need from the encodings to say that this step goes through. And then they show if you have these things, and then you have an appropriate group that has some kind of subgroup decision type things going on, then you can get sort of full security for your scheme. Yeah, so that was nice because it simplifies constructions. Also, it allowed for construction after, there were a couple more works, but it allowed for constructions in prime order groups, which are quite, can be quite challenging because they're even more complicated. Subgroup decision in prime order groups is more subtle. I gave nice basic AB under decision linear, SXDH. It also gave a way to sort of capture a bunch more features, but the initial work on that required a computational property. So in order to go, the first works were nice because they had sort of an information theoretic step. So this showing that you could go from add this beta was just an information theoretic property you had to prove, which makes it nicer to prove, and it's shorter proofs and easier to verify. But if you wanted some of the more complicated features like compact ciphertext or some of the, I think, unbounded attribute sort of things, then you needed a computational property. And that meant you had to go back to not just looking at the exponents and looking at this information theoretic thing, you had to go back to a reduction to a computational assumption. And that again, now you've got several pages of proof just to prove that one property again. So we had to work in 2017 that we call symbolic security, which tries to get sort of the best of both worlds. So it's an information theoretic property on these encodings. And you could say that if this property holds, then you get full security. And the other interesting thing is we can say that actually if your encoding is not trivially broken, as in if there's no obvious way to take the encoding and the key encoding and the ciphertext encoding, when the key doesn't satisfy the ciphertext, and put them together, just a bilinear operation and get out the secret. If it's not broken in that kind of trivial way, then the encoding will satisfy symbolic security. So really, you just have to design something that's not obviously broken, which you think that might normally be the case, but really constructing things that we can prove secure in the ABA setting is not easy. So you actually, in general, have to do a lot more work and come up with something that's considerably more complex to get something that you can prove secure. And so the nice thing is here we can say, like, as long as it's not either there's a trivial attack that just applies the pairing and pops out the blinding factor, or the thing satisfies symbolic security, which I think is nice. And that also allows us to capture AV with a lot of the fancy advanced features under a Q-type assumption. I think one of the interesting sort of open questions that I would love if somebody looked at is there a way of sort of doing this, of getting something that's so simple, where you can say, like, all you have to do is sit down and make sure that you can combine these elements and decrypt if get the master secret if the policy is satisfied and not if not, and get this kind of result under SXDH or DLAN, because that's something that we were not able to do anyway. Okay, so sort of moving a little bit forward in time, I think it's sort of the last stretch of years, we're sort of getting very close to the best of all worlds. We have pretty optimized constructions. They're actually getting nice and simple. They're getting more efficient because they're getting simpler, and the analysis is getting simpler. And we also have a lot of the features we've looked at, and again, those are getting better. Simple assumptions, we can get most of these constructions now based on SXDH or DLAN. We don't need composite order groups anymore. I think the one open question is, it's still fairly challenging to design and prove security if you want to add a new feature. So I think particularly some of the new fancy techniques, if there were a way to sort of incorporate those into the generic constructions, that would be cool. But yeah, I think we've actually come a long way. We're in a pretty good place as far as constructions are concerned. So I guess then I wanted to turn a little bit to sort of the practical side, because that's a little bit more where I live these days. So there's been a number of applications proposed for this. So people said, oh, maybe we can use them to encrypt medical records. Maybe we can use them to encrypt your social network. Maybe we can use them for sort of cloud services. Right. But what I was going to say is so there's a number of applications, and I think it's because it's sort of easy to think about, it's a nice way of storing your files encrypted in the cloud with an access policy attached. So it's sort of access control, but encryption enforced. So I guess one question you could ask is sort of why don't these things exist yet? Like why is it taking, and they do now, but it's very recent that these things have been deployed on a wide scale, and why not? Because it's a really cute thing, and we can see what the application is. And I think there are a couple of reasons. So one is sort of technical. So I think, it's hard to revoke access once you've given out a decryption key. And there was one work that tried to address this, but so that's one challenge. So normally if you do things where it's more access control based, so you have a server that controls access, stores all the secret documents or whatever it is, and you go to the server and say, here's my permissions, here are my attributes, I should be able to decrypt this file, and they allow you to decrypt this file. So that's really nice from a revocation point of view, because if the server you don't have those attributes anymore, the server just doesn't give you the file back. So it's whereas once you've given out this decryption key, it's really hard to take back decryption ability. And I guess also, like, if the user downloads the entire database, then even if you revoke their credentials later, that's not going to work. I think the other maybe bigger reason for why these aren't used is that there is an alternative, and it's sort of right. Let's see. Right. So this is sort of the this is how these applications sort of work. You have a bunch of files encrypted in the cloud. You have people who want to encrypt, so they look up the key server's public key and they encrypt under their policy. And then you have these decryptors who have their secret keys. Okay, but I think that the thing is that you can actually get something close from public key encryption. It's not as good, but it's sort of good enough in a lot of cases. And the way that works is you just have a central key server. It's sort of what I was talking about. You have a central key server. You encrypt everything just under that public key, but with the policy attached. And then every time you want to, so say the policy is like in the tag or something like that. So now when, say, the doctor at hospital B wants to decrypt this file, they go to the key server and they bring their encrypted file and they bring their credentials and they say, this is me, I should be allowed to decrypt this file, and the key server helps them to decrypt the file. It's not as elegant. It requires a central key server, but in a lot of cases, that's not that hard to build, and it's much easier because you only use existing solutions. So you only use existing public keys. So you only use public key encryption. It's standardized. You don't need any new libraries. It's pretty easy. And having a key server running, maybe not that bad. So I think the only downside is that we have to go back to this key server every time. But in some cases, that's not a big problem. So I think what was really interesting is this Cloudflare application so Cloudflare is actually using ABE on a global scale, which is awesome. And it sort of points out really nicely, like, where it's a really nice example of where sort of this having a central key server is a problem. And so where ABE is really well motivated. So this sort of trivial public key solution doesn't work. So the application I'll just give you, so I'm going to say I'm not involved in this at all, but I think it's really cool, which is what I'm talking about. So the application is the Cloudflare rather. They run endpoints for different companies as TLS endpoints. So the users connect to a Cloudflare server instead of a particular company, and they want it to look like you're connecting to that company because they're going to serve data on behalf of that company. So they need to store sort of TLS keys for that company, and the part of what Cloudflare's business model is they make your data sort of globally available. So you have one set of data, you give it to them, and they sort of distribute it so that everybody can get it fast wherever they are in the world. So that means that I want that if I'm in Taipei and I want to access the data, I go to the nearest server, I get back the data. If I'm in Seattle, I also go to the server and get back the data, the nearest server. So whatever West Coast server there is in the US. So what that means is that you need these TLS keys to live, ideally on those servers. And it should look the same everywhere. So you're taking the customer's secret TLS keys and you're putting them on the Cloudflare servers. So that means, well, first of all, you want to store them encrypted. You also, I want to be able to access those keys, here in Taipei and back in Seattle. But well, the server should be able to access those keys. But they should only be, there's often restrictions where the companies say, well, I only want my key to be accessible to machines or data centers that satisfy certain policies. So maybe they should only be accessible in certain regions or certain countries, or not in certain countries, or only things that satisfy a certain standard, some compliance standard or a security level or something like that. So I guess figuring out how to manage this was a big problem. And that's where they ended up using attribute-based encryption. So basically the idea is they take these TLS keys and they already have a system for distributing data across the world. That's what they do. So they can encrypt the TLS keys, and they can make this database accessible from this is the picture from before, but from anywhere, any data center in the world. That's on the next slide. This one. Yeah. So from any data center in the world, so every data center essentially has its own copy of this database of the encrypted files. So it's just a matter of them being able to decrypt the files and making sure that only the right data centers can decrypt the files. So I guess you ask, can we build this from public key encryption? We could. So again, we could have this key server, and you encrypt, you just encrypt with public key and use the policy as the tag. And then they go back to the key server and get a decryption. But where does this key server live, I think, is the interesting part. So, we could distribute the key server. Now we got, again, the same sort of problem, or, plus major trust issues. Or we could have a central key server, but now everybody has to go back to this key server, so that you're going to have major latency, because everybody has to contact the same key server every time they want it. All of these data centers, every time they want to serve a client request, they're going to have to go back to the key server and say, please help me decrypt the file. So that's sort of a problem for latency reasons. It's also like a bottleneck. If that key server is in a data center that goes down, now you've got major issues. So that's single point of failure and increased latency, but neither, which is good. So that's where AV is really nice, because now this sort of trivial solution, which is good enough for a lot of applications, is not good enough. So actually what they do is they use attribute-based encryption. So the customer encrypts their files under this master public key using the policy they want. So say region is Europe and security is high or something like that. And then each of the data centers, when they boot up a new machine, they can get a secret key for that machine that corresponds to the attribute. So security level this, region this, country this, blah, blah, blah. And then we already said that they have a nice way of pushing the encrypted ciphertext to all of the data centers. So now when the client contacts a particular data center and gets routed to a machine, the machine already has a decryption key, and it already has all the files encrypted, so it can just immediately decrypt, get the TLS keys, and answer the request. Great. That's what I just said. Yeah, so this is really nice, and I think it's a nice example of where AV perfectly solves the problem. They actually do some more work that's sort of hidden to make it easy to rotate keys, because again, there's that revocation problem. They solve it somewhat with key rotation, and also to make it a little bit more efficient. So they describe it as a little bit like hybrid encryption, but they don't generate an independent secret key for every machine in the data center. They actually sort of reuse the private keys when multiple machines have the same attributes. Maybe it's on the public key side as well. Anyway, so that makes things a little bit better. Yeah, so oops, sorry. So that was all I was going to say about the application. I think the blogs about it were in January of this year, so it's fairly new. I think it's still in beta, but as I understand it is being used on a global scale. And then I guess, so that sort of sums up. I think AV has come a long way from 2005. We have lots of features. It's been almost 20 years. Lots of features. We have nice security guarantees, good assumptions, efficient constructions. Still somewhat challenging to construct and prove security, but there's been some work on that. It's also had a large-scale deployment, which I think is exciting. And I guess the cool thing is to see what comes next. I think now that we have a deployment, there will be new interesting problems that come up, and when we see what the challenges are there. So I'll stop there. Thanks for listening.
Do you have any questions from the audience? Maybe I'll start with a question. Well, so I want to take us back a little bit in in history since the Test of Time Award. So sort of this ABE notion was introduced in 2005-ish. In fact, that was then just for the IBE, right? And then the ABE really was 2006. So it's just 1 year after that. And your paper actually came out in 2007, which meant that you must have started working on ABE as soon as it came out. So as far as I know, at that time you were working with Anna and mostly on anonymous credentials and related topics. So how did you come to be working on ABE then?
Oh yeah, that's a good question. I think it's been a long time. I think I ended up reading the paper and I think reading group or reading class or something like that, and I thought it was interesting. I think I could be wrong, but I want to say Sahai and Waters actually sort of mentioned attribute-based encryption as like a possible application in the end. They don't have policies, but as something another way you could view or use these fuzzy ABs. And I think because I was already looking at credentials, which credentials, it's really natural to think of different authorities give credentials, for different attributes. That's sort of how the anonymous credential world works. So you want to say, exactly this kind of thing. So I go get a credential saying I'm this old, and I go to get a credential from the DMV and another one from the university to say I'm a student, and then you want to be able to put them together. So I think that's probably led me into multi-authority AV. Also, I thought it was a cool, cute, playing with, it was my first exposure to pairings, and that also, it's sort of fun to play with. Proofs and stuff.
I guess that kind of answered my question, my follow-up question, which was whether there was a specific trigger that led you to this multi-authority notion. And it sounds like really it came naturally from the credentials perspective then?
I think so. I actually don't remember that well because it's been a long time, but I think so. Yeah.
Okay, thank you. Let's see if the audience has more questions.
Maybe, hi. Yeah, thanks for the great talk. So, in the large body of work on ABE, a lot of it focuses on theory-oriented questions like, selective security, the exact type of assumption, and so on, whereas I guess that practitioners might be happy with solutions using generic bilinear groups. So my question is, if you consider generic model, which people are happy to use, say, in the context of snarks, what would be the challenges or maybe one, if you can mention one nice open question that is possibly practically relevant about ABE using generic bilinear groups?
I don't know. I mean, I think.
In what way can we make the current state of the art better if we are willing to assume a generic bilinear group?
Yeah, that's a good question. I feel like we're pretty far along in terms of constructions. I don't really feel so. I mean, I'm sure the folks who are working on it have a better answer. But in terms of, I feel like we can construct most of the things. Maybe you could optimize a little bit. You can probably shave off some elements. But we actually know how to construct a lot. A lot of the work now is like improving the proofs. I think one thing that would be cool is proving things in a generic group model is terrible, right? So every time you construct a new property, you have to generate, and these proofs, the schemes are still somewhat complex. So writing out that proof and verifying that proof as a reviewer is not fun. So if there's any nice way of abstracting that out so you don't have to do so much work on the proof side, I think that would be nice. It would make it much faster to generate, whatever weird combination of features you want for your particular application. If there was a way to do that without writing a 60-page paper or 30-page paper or whatever, that would be awesome. But yeah, I don't know that much about major open works. I guess the revocation question is sort of interesting. There was this one work that I know about. I don't know of anything else on that. And that work is fairly expensive. So there was a nice way of sort of, rolling keys. Like I said, the Cloudflare has a sort of a construction where they put together some public key encryption and some AB, and it works for their application, but having something more generic would be cool.
Yeah, sorry, can I ask one more question here? Up here. Have you thought about sort of other cryptographic primitives that we could make attribute-based, or do we already have that? Like, I don't know, an attribute-based signature scheme, I guess that's very close to credentials, or some sort of attribute-based MPC. I don't know, like is there something, do these things just not make sense, or do they already exist? Yeah, do you have any thoughts on making other cryptography basically not based on fixed roles but attributes?
Yeah, I don't. I mean, anonymous credentials is one thing, I suppose. And so that's or attribute-based credentials, whatever you want to call it. But that's one place where you are again. You're proving not I'm the owner of this public key, but I'm a person who has this entity is certified that I have these attributes basically. So that's sort of related. There has been work on attribute-based signatures. I don't know of other. I don't know of other. I haven't found other great applications, but they might exist. And maybe just I haven't thought of it.
All right. Let's thank Melissa again. Any question? Sorry, any announcements from the local chairs?
Hello. Lunch, the most important thing, of course, is in the same place on the fourth floor. And we received notification that some people brought food and drinks into the conference room. Please don't do that. If you see other people do that, stop them or tell us to stop them, because the penalty is pretty high if like we got caught doing that. Thank you very much. will.
然后开屏报，哇，如果等下那个最后一场是 2D 的话，就按他两个都写，会有下个好，主要比赛都是要到多少点？大家说这个场外就是走到。现在手是谁？现在是啊，OK OK。然后什么比就最后一场应该就最后一场应该就他们统一这台吧。对。再分析一下A跟 C。对，差不多这样。
Welcome to encryption session. We have 5 talks in this session. The first talk is Case, a new frontier in publicly authenticated encryption. Manoj is going to give a talk.
Thank you. So this is joint work with Shashank Agarwal, Shweta Agarwal, Rajiv Rekhnad, and Jair Singla. And what I'm going to tell you is a new way of doing public key authenticated encryption. So I'll begin with what is CASE. So CASE stands for completely anonymous signed encryption. So it's a little bit like signed encryption, but our focus is on security. And it involves a sender who can use an encryption key for the receiver, their own signature key, signing key, and create a case packet. A case packet is the analog of a ciphertext, and send it out. And if a receiver has a decryption key and a verification key corresponding to the sender signing key, then they can retrieve the message and authenticate it. And we'd like to consider an adversary who's not just passively eavesdropping on all of this, but can also create malicious case packets, malicious public keys, and even malicious private keys, and get honest users to use them. And even in the face of such an adversary, we'd like our primitive to stay as close to ideal as possible. So what is ideal case? So you could think of it in terms of a trusted third party or a trusted database. So the honest users, the senders, receivers, many of them, they can create idealized objects. Their idealized objects are created inside the database by the trusted party, and it just gives out handles to the users to operate on them. And similarly, the adversary can also create these objects, get handles, and they could also transfer their handles to each other. So the honest users can transfer some handles in their views to the adversary, and vice versa. And they can also talk to each other freely outside of this interaction with the trusted party. Okay, so that's what you would expect as an idealized world for authenticated encryption. And the kind of operations are what you would naturally expect. You can create key objects, idealized objects, case packets, and if you have the right kind of keys, you can decrypt them, so open them, retrieve the messages. You can compare two objects and so forth. So it's a little bit like you could think of it as a generic group model kind of setting. Okay, simple as it is, it comes with a lot of implications. So, for instance, so of course, some of them are more obvious than the others. So you cannot find out what's a message inside a case packet if you don't have the decryption key. You cannot even tell who the signer is or which signing key was used, even if it was your signing key, a signing key that you maliciously created. Unless you have the decryption key, you cannot tell this. And even if you have the decryption key, if you don't have the verification key, you cannot tell which signing key was used, and so forth, right? Or you create two case packets using maliciously created keys, they will not accidentally turn out to be the same case packet. They will stay different. So we collect a bunch of these requirements and form this definition called chosen objects attack security. It's a little bit like chosen ciphertext attack in PKE, but beyond ciphertext or case packets, we also allow the adversary to create their own malicious keys. So it's chosen objects. You can create all the objects maliciously. And these requirements are, there are a few game-based definitions, so total hiding, sender anonymity, strong unforgeability. And there are a few other requirements, of course, correctness, unpredictability, and existential consistency, which essentially says that a case packet can have at most one set of public keys associated with it, and a public key can have at most one private key associated with it. Okay, so fairly natural set of requirements, but you should ask, is this comprehensive? Did we miss out any requirement, right? And that's where the next part of the work comes in, and that's this framework that we call active agents framework. So what we'd like to do is to have a real ideal definition, the real ideal paradigm, to make sure we are not missing out on any subtle attacks that we don't think of. And we already saw what ideal case is. That's easy enough to define. The tricky part is, what does it mean for something to be like ideal? What does it mean for a real implementation to emulate the ideal situation? And the difficulty is because simulation-based definitions, which is what you would naturally go for, turn out to be impossible. Okay. So what we do is use something called indistinguishability preserving security, which says that if two behaviors of the honest user, so they're called test here, so two behaviors, test 0 and test 1, if they are indistinguishable from each other in the ideal world, then that should be the case even in the real world. Okay, so that's indistinguishability preserving. And this is a definition we used in the cryptographic agent framework, which is something some of the authors in this work introduced in a few years back. And that was in the context of primitives like obfuscation, functional encryption, where we only considered a passive adversary, an eavesdropping kind of adversary. Here, we also want to consider active adversaries. We can create malicious objects. So that's an extension to the framework that we do here, and that's what's called the active agents framework. Now, even with this relaxation that we don't want simulation-based security, just indistinguishability preserving security, things still remain impossible to realize. So we need to make a couple of more restrictions. And one is we don't consider all possible behaviors of this test, only something called delta tests. And also we only require statistical indistinguishability in the ideal world to be preserved as computational indistinguishability in the real world. So with these restrictions, we get a definition called delta S int pre security. And this pretty much covers all sorts of indistinguishability game-based definitions that you would come across, things like CCA security or anonymous CCA in the case of public key encryption. Now, of course, here this is not this is for case, not PKE. Nevertheless, the delta S in pre-security definition, which says real and ideal, and how real and ideal should be like each other, doesn't really care about what the primitive is, right? What exactly the primitive is all captured in the description of the ideal. So it's like the functionality in this world. So it's not all fitting to just the attacks we thought of. Right? It's a general security definition. And the main theorem, and most of the effort in this paper went into proving this, is that this list of properties that I listed in the beginning actually implies the security guarantee, the delta S in pre-security guarantee. Okay. I'm not going to go into the proof of that. It's very tedious, but and of course, it's because of that that we wanted to prove this, that particular list of properties is what we ended up with. Okay, so we do have a comprehensive security definition, and the next question is it achievable? And sure enough, it is. And our starting point is standard, traditional public key encryption with anonymous CCA security. And we also require a property called quasi-deterministic determinism. So this is essentially already achieved by Kramer-Shoup encryption, for instance. And the quasi-determinism property is just that the ciphertext comes in two pieces. The first piece entirely encodes the randomness, doesn't depend on the message. And the second part is completely determined once you have the message and the first part, information theoretically determined. And from this, from Kramer-Shoup, we build something called COA secure quasi-deterministic PKE. So it's a little bit like our COA secure case, but simpler because it's only PKE. And then we use that to also do something to signatures. We get anonymous signatures, which have this existential consistency property I mentioned. And we use both of these things together to finally build our case construction. Just to very quickly mention, to get from PKE to COA secure PKE, we need to add existential consistency. That's done carefully by adding commitments. Nothing too complicated, just need to be careful to avoid circular security kind of issues. And you can get this. And to get anonymous signatures, you add a layer of encryption, but the encryption is using a key, a public a key, the secret key is part of the verification key. So some encryption that you can remove if you have the verification key. And again, we need existential consistency. We rely on quasi-determinism here to say what we are going to sign is not just a message directly, but the message and the randomness used for the layer of encryption. That randomness as encoded by the first part of the ciphertext. And you put them together into case carefully again. And here again, you start encrypting, so you create the randomness part, then you sign the message and the randomness together, and then you finish encrypting. And then signature scheme used is this one, and the encryption scheme used is this one. And it turns out it all works. And it's not necessarily the most efficient one if you're counting the number of group elements, but doesn't really matter for large messages because a hybrid encryption works, retains all the security properties we need if you do it properly. So you would use symmetric encryption and the quotient-resistant hash function, and the keys of the encryption and the hash are what you encase, what you put in the case packet, and the rest of the message itself is encrypted using the SK. Okay, so it's not just achievable, it's quite practical too. And we hope it's something that can be implemented and actually used in practice. So these boxes you get at the end are fairly robust. You can throw it into any application, and hopefully it'll behave as ideally as we can get them to.
We have plenty time for question. So if you have. So is your construction is analyzed in the agent framework? Is there any relationship agent framework and the UC framework?
Yeah, so the agent framework doesn't use simulation. So it's inspired by UC in the sense of real ideal, but it's its own definition. That's delta S in pre-security.
Thanks. Any other question? No. Okay. Let's speak again. Okay, the next talk is lower bound on assumptions behind registration-based encryption, and Sarah is going to give a talk.
Hi everyone. Today I'll be presenting our work, Lower Bounds on Assumptions Behind Registration-Based Encryption. This is a joint work with my supervisor, Mohammad Hajiabadi, Mohammad Mahmoudi, and Waiki. So let's start with a quick review on public key encryption. Here we have Alice and her friend Bob. Alice wants to send Bob a private message, so Bob needs to have a public key and a secret key pair and send his public key to Alice, which Alice can use to encrypt her message and send the ciphertext to Bob. And then Bob can later use his secret key to decrypt the ciphertext and retrieve the message. Now, something that's really important to note here is that Bob's public key could be something like this, which is really hard to memorize or remember. So later on, another friend of Alice comes, Charlie, and she also wants to send Charlie a private message, so she asks for Charlie's public key and then encrypt the message under that public key and send that to him. Later that day, Alice finds a new friend, Daisy, and she repeats the same process with Daisy, but Alice gets tired because this is just too many public keys to handle. Now, this may actually work in theory, but it needs an expensive key management infrastructure, which we don't like. And that's exactly why in 1986, Adi Shamir proposed identity-based encryption. So in identity-based encryption, we again have Alice and we have Bob, But this time we also have a third party called private key generator who generates a master secret key and a master public key or a public parameter. So now if Alice wants to send Bob a message, she can easily encrypt the message under Bob's identity, which could be his name, email, or something like that, and a public parameter, and send that to Bob. And when Bob wants to decrypt it, he should in some way prove his identity to the private key generator, who will then issue a secret key for Bob, and then Bob can use the secret key to decrypt the ciphertext and retrieve Alice's message. Now, this is really nice, right? Because Alice can now send all of her friends private messages without needing to know everyone's public key and only knowing one value, which is a public parameter. But then there's a new problem, and that's what if the PKG is compromised? So IB is known to have a problem called key score problem, and so it means that we know that the private key generator has access to the master secret key. So he can generate all of the people's secret keys and then use the secret keys to decrypt ciphertext for everyone. So that means that we need to put a lot of trust in the authority, but it's not reasonable to give too much power. To give too much power to a third party. So that's why registration-based encryption was proposed. It was actually introduced by Garg, Hajiabadi, Mahmoudi, and Rahimi in 2018 to address the key score problem of IBE. So in registration-based encryption, the private key generator who generates secret keys is replaced with a public key curator who aggregates public keys. This public key curator is totally transparent and has no secrets. And also, all of the users generate their own secret key in public keys. So let's take a closer look at the registration-based encryption. Like I said, the private key generator is replaced with a public key curator. So when Bob joins, what Bob needs to do is to generate a public key and a secret key pair for himself, and then send his identity together with his public key to the public key curator. And the public key curator will then run a publicly computable aggregation function on Bob's identity and Bob's public key, and then publicly announces the output, which is the public parameter or PP1 here. After that, Charlie joins. Again, he will generate a public key and a secret key pair for himself, and similarly, he will send his identity and his public key to the public key curator. Public key curator will again run his aggregation function on public key of Charlie and Charlie's identity and the previous public parameter, and then announces the new public parameter, which is PP2 here. So now, if Alice wants to send Bob a message, she can encrypt the message under Bob's identity and the public parameter. But how can Bob decrypt this? So in order for Bob to be able to decrypt this message, the public key curator will need to send Bob a hint or an update, which is, by the way, totally public and is only a function of the public parameter and Bob's identity. And then Bob can use this hint together with the secret key to decrypt the ciphertext and retrieve the message. So how do we construct an RBE scheme? Let's say that we have n users and their public keys are pk1 through pkn. Then there's a trivial RBE scheme in which we can set the public parameter to be all of the public keys of all users concatenated with each other. And then if we want to encrypt a message for someone with identity I, we can easily encrypt the message with the ith public key. And the ith person can obviously decrypt this message successfully. But this is not interesting at all, because here the size of the public parameter grows linearly with the number of users, but the whole point in using IBE was to have a single compact public parameter instead of all of the public keys. So we need to set some limits on the RBE to be efficient. Again, suppose that we have n users. So what we want is for the public parameter to be compact, meaning that we want the public parameter size to be polylogarithmic in terms of n. We also need to set some constraints on the number of updates or hints that each user receives, but it's not in the context of this talk. So now, with this new efficient definition of RBE, let's look at the existing constructions. So the original paper that introduced RBE constructed RBE from indistinguishability obfuscation, and the subsequent work built RBE from garbled circuits. But both of the works used their side assumptions, which was LWE or CDH, in a non-black box way. So at that time, we knew that RBE can be constructed based on basic assumptions like LWE or CDH. Then what are we looking for? What is the problem here? So generally, non-black box constructions are less efficient than black box constructions. So even if we know how to do something in a non-black box way, it's always a good idea to go after black box constructions. So let me tell you what we have about black box constructions. Hohenberger et al. And Glaser et al. Both constructed RBE in a black box way from bilinear maps. But assuming a common reference string or CRS, whose length can grow with the number of registered users. Now, something that's really important to note here is that this CRS is not an input to the encryption algorithm. The encryption algorithm only depends on the public parameter, which is still compact and independent of the number of users. Also, Duckling et al. Constructed RBE in a black box way from LWE. So now that we know that RBE can be constructed in a black box way from bilinear maps or LWE, the question is that can we also construct RBE without those assumptions? Or in other words, what are the minimal assumptions for black box constructions of RBE? So in our work, we showed that RBE cannot be built in a black box way from trapdoor permutations or in Shoup's generic group model. And both of these impossibility results also hold even if there's a CRS whose length can grow polynomially with the number of users. The one thing that you might ask yourself is that why did we choose these assumptions? Why trapdoor permutations in Shoup's generic group model? So the reason is that we know public encryption is necessary for building RBE in a black box way. But the question is it also sufficient? So if we rule out black box construction of RBE from TDP, we also rule out black box construction of RBE from any primitive that can be built from TDP in a black box way, including collision-resistant hash function and public encryption. So by ruling out black box construction of RBE from TDP, we can answer the first question with a no. Also, similarly, if we rule out black box construction of RBE in the generic group model, we can rule out black box construction of RBE from assumptions that hold in this model, like decisional Diffie-Hellman, or even stronger assumptions. Another thing that you might ask yourself is that can't we just use the previous separations, black box separations for IBE? Because we know that IBE cannot be constructed in a black box way from trapdoor permutations or in Shoup's generic group model. So don't these results just immediately apply to RBE? The answer is no, and that's because we don't know if RBE implies IBE in a black box way. We do know that it implies IBE in a non-black box way, but this connection is not sufficient to rule out those constructions and prove the separation. So we're going to prove our separation with respect to a black box equivalent of RBE called public key compression or PKCOM. And instead of using the combinatorial ideas that are behind the existing IBE separations and are not applicable to our settings, we develop new compression techniques and use them to prove our separation. So what is this public key compression? The difference between public key compression and the regular registration-based encryption is that all of the users join in parallel in the public key compression. So the users will first generate their public key and secret key pairs, and then they will send their identities and their public keys to the public key curator at the same time. And the public key curator will only run the public aggregation function once and outputs the public parameter or P. Now, this version may look weaker, but it's actually black box equivalent of RBE. So our impossibility results also generalize to RBE. So let's talk more about the high-level idea behind our proof. Let's say that we have a TDP oracle with three algorithms, G, E, and D. G takes as input a trapdoor key and outputs an index key. And let's call an index key valid if it's in the output space of the oracle G. So the main thing that we're going to prove and use in our proofs is that compacted strings cannot signal too many trapdoors. And in order to prove this, we use a lemma called compression lemma, which I will explain very informally here. So we have this TDP oracle, and we have an adversary who can query this oracle as many times as he wants. And after all of these queries, he should output an advice string or PP with size less than n and send that to another adversary, Eve. Eve can also query the TDP oracle, but this time we can only query the oracle polynomial number of times. And at the end, he should output a list of index keys. Now we say Eve was successful in this game if this list has two conditions. First of all, it has n distinct valid labels, and then none of these labels were generated as an output to a query that Eve has made to G before. So the compression lemma says that probability of success for Eve in this game is negligible. And we proved this based on the compression techniques that were initially introduced by Gennaro and Trevisan. So now we proved that compact strings cannot signal too many traps. And we can use this to show that a public parameter of size less than n cannot embed n public keys. So for at least one identity, the message is encrypted to that identity can be decrypted using secret keys of other people. And that proves our black box separation. So let me quickly tell you how our work is different from prior impossibility results on IBE and why those techniques don't apply here. So the existing IBE separation proofs rely on the fact that the running time of setup algorithm that generates master secret key and public parameter in IBE is bounded. But in fact, in RBE, the running time of the algorithm that generates a public parameter could grow with the number of users. So we can't use the same techniques to prove that a compact string cannot signal too many trapdoors. For the generic group model, we also use the same approach, which I won't explain here because of the time constraints. But we informally proved that a compact public parameter cannot encode enough information to securely encrypt more than a bounded number of users. So to conclude, we proved the first black box separation of RBE, in which we say that it's not possible to build RBE in a black box way from trapdoor permutations or in Shoup's generic group model. And we also developed new compression techniques that can be used individually. And that's it. Thank you.
Time for question. Is there any question? Let's thank the speaker again. The next talk is security with functional re-encryption from CPA, and Shai is going to give a talk.
Thank you. Right, so I'll talk about security with functional re-encryption from CPA. That's a joint work with Evgeny Dodis and Daniel Wicks. And what I'm going to talk about is the notion of security called functional CPA, which is a notion of security for encryption scheme that lies somewhere in between chosen plaintext and chosen ciphertext security. That notion was introduced by Akavia et al. In TCC of last year. And roughly speaking, it's very similar to CCA in the sense that the attacker gets an oracle that it can query, but instead of decrypting, this oracle does re-encryption. It decrypts and then re-encrypts and sends the result ciphertext back to the adversary. Actually, you can get a little more general than that. You can make a functional re-encryption queries. That is many ciphertext and a function, and then the oracle decrypts all of these ciphertext, applies the function, and encrypts the result. What's interesting about this notion? Isn't it just simply implied by CPA security? After all, the attacker only sees valid ciphertext. Turns out that that's not the case. Akavia et al. Had a surprising example of a CPA secure scheme where a single query to a re-encryption oracle reveals the decryption key. And the point is, the adversary can send invalid ciphertext to be decrypted and re-encrypted, the decryption query can do very funky things on these invalid ciphertext, so funky that even once you encrypt them back, it's still a security problem. So that makes functional CPA an interesting notion to study, and it's on even beyond the original motivation that Akavia and Al had for fully homomorphic encryption type. So I want to spend a minute showing you why that notion might be interesting even when you're not talking about homomorphic encryption scheme. So imagine that we want to, that I want to set up a secure enclave to carry computation. So the enclave will have a key inside of it, and clients can send encrypted things under the public key, and then perhaps a function, and the enclave will do exactly what the functional re-encryption oracle does. Decrypt, because it has the secret key, apply the function, and send back the result encrypted back to the client. And you can repeat that. So that's exactly the functional CPA attack model. And just like in CCA security, you can think of all kinds of settings where you want to protect things against a client like that. Either there are multi-user setting and some users can be adversarial, or a network adversary that can play man in the middle, or send ciphertext to be re-encrypted. So what we ask in this work is, where does it lie? So it's very easy to see that it's implied by CCA security and implies CPA security, but is it closer to one or the other? Can you construct functional CPA secure encryption just based on CPA secure encryption? Or can you construct CCA secure encryption based on functional CPA? And while we're at it, can you do it with a black box transformation? So in this work, we show that functional CPA is closer to CPA security. The theorem that we prove is that func CPA secure encryption can be constructed from any CPA secure encryption via black box. The main technical observation is that you can take transformations from the literature that were introduced in the context of transforming CPA secure encryption to non-malleable secure encryption, and use them also in the context of functional CPA security. But the adaptation is not straightforward, because those techniques were devised for non-adaptive decryption queries, and here we need to use them in the context of adaptive re-encryption queries. And I'll explain about it in a couple of slides. But for now, let's look at the definition of func CPA encryption. So the adversary gets an oracle, and that oracle is either this functional re-encryption oracle that I talked about before, that decrypts everything, applies the function, and then re-encrypts, or just a worthless oracle that encrypts always zeros. And the adversary's job is to tell which is the case. And the advantage of the adversary is how much it can get better than a random guess, and it would be secure if the advantage is negligible. So that's a natural definition. And the main tool that we use in order to show that you can construct things like that from CPA secure encryption is this transformation of Cho et al. I guess 2018 was the journal version. It's a transformation from 2008, if I remember correctly, that describes a black box construction of non-malleable encryption from CPA security. So very quickly, non-malleable security is very similar to CCA security, except the adversary only have a single decryption query that it can use. It can ask for as many ciphertexts as it wants, but only once. So just like CCA secure encryption, you have the public key, you have the two target plain text, one of them gets encrypted, then the adversary gets to use its decryption oracle, but only once. It can query for a vector of ciphertext as long as it wants. It gets the corresponding plain text, and then it needs to guess whether the PK, the plain text 0 or plain text 1 were the ones that. What we show is that the exact same transformation yields functional CPA security, but only if the underlying scheme is already non-malleable. So if you want to get a functional CPA encryption, secure encryption from CPA secure encryption, then you could apply once the transformation to get non-malleability, and then apply yet again to get functional CPA. Now, I'm not going to have time to show you the transformation at all, but I will give you a hint about what the difference is in the proof of security from the original Choi et al. So valid ciphertext after that transformation has a certain structure. And in the analysis in the proof of security, there is a bad event in which the adversary sends for the decryption oracle invalid ciphertexts, but the decryption procedure fails to detect that these are invalid. And as long as that bad event doesn't happen, then the rest of the proof is fairly straightforward. So the main thing is to show that this bad event rarely happens. And in the original transformation to get non-malleability, you can actually have an information theoretic argument saying that this bad event almost never happens because each public key has associated with many different secret keys. Most of them, almost all of them, will detect that for every fixed invalid ciphertext, almost all of them will detect that this ciphertext is indeed invalid. And until the adversary uses its decryption query, it has no idea which of them is actually used. So really, it cannot send, almost never, this invalid ciphertext that will not get. And that's enough to show non-malleability. But in our case, we need to handle adaptive oracle queries. So the adversary can send queries, and then the query will either detect or not detect that it's an invalid ciphertext. And based on whether or not it detected, the adversary can get some information about what secret it is. However, the question of whether it was detected or not is sort of hidden behind the fact that the adversary doesn't get the decryption. It only gets a re-encryption of that. So it's hidden behind the encryption. What it boils down to is we cannot have an information theoretic argument anymore. We need to go for a computational argument, namely a reduction. So we need to have a separate reduction showing that the bad event doesn't happen based on the CPA security or the non-malleable security of the underlying encryption scheme. And the idea here is, well, we need to set up a reduction. The reduction does need to know whether or not the bad event happened. How can we let the reduction know whether it happened or not? Well, obviously, we can, if we give the reduction a decryption oracle, then it can check for itself whether the bad event happened or not. But the point is, it's enough to give it a non-adaptive access to the decryption oracle because the reduction can run the whole game all through the end, and at the very end, just take all the ciphertext that the adversary ever submitted and ask the decryption oracle to decrypt. In other words, we get a reduction to the non-malleability of the underlying. So with that, I'm more or less done. We show that applying this transformation of Choi et al. Twice yields a functional CPA secure encryption, starting from a CPA secure encryption. Whether or not we really need to apply it twice, well, we don't know. On one hand, the reduction that we describe absolutely needs the underlying thing to be non-malleable. We don't know how to prove it from CPA security if you only apply the transformation once. On the other hand, we don't have a counterexample, and in fact, we have some arguments saying that a counterexample cannot be too simple, whatever that means. Are there other transformations that are simpler? We don't know that either. Maybe for the special case of non-functional re-encryption, you don't apply it. Perhaps, we don't know. And of course, whether there are other applications of that security notion. That would be nice to know. So that's all.
Time for questions. Is there any question?
Yeah, Shai. So how specific is the CDMW technique for your result? Like if I gave you a generic black box transformation from CPA to non-malleable and you applied it twice, would it give you this?
So I can't say about every transformation, but every transformation that we know of would work. So there are like 3 or 4 different transformations in the literature, and each one of them, if you start from a non-malleable secret and apply that transformation, you get functional.
Do you know
it's
what is?
Actually an interesting question of whether it's generic. I don't think it's generic, honestly.
You can't say what the property is that you use.
the only thing that I say, the only thing that I can say is what I had in the slide. There is bad event and current transformation work this way. So yeah.
Other questions? Let's speak again. Okay. The next talk is revisiting updatable encryption, controlled forward security, constructions, and punctuable perspective. And Roman is going to give a talk instead of the authors.
Yeah, thanks for the introduction. So this is a work by Daniel Lammerning and Christoph Strix, who unfortunately both could not attend, so I will present on their behalf. So I'm sure you all very well know if you use a public key encryption scheme, only the public key is supposed to become public. That sounds very easy in theory, but in practice, unfortunately, mistakes happen, usually due to human error, and sometimes also the private key is leaked. So these are just two of countless examples where this happened. And that usually is a disaster, because if your key leaks, then everything that has been encrypted under this key is in danger. And one strategy to mitigate the damage of such a key leakage is forward security, which basically just means we want some guarantees that old data is safe even if your key gets leaked at a later point. And for example, this has become mandatory in TLS 1.3, and also all big tech companies have recognized the importance of this. And several cryptographic schemes have been considered in a variant that provides forward security. So for example, key exchange, public key encryption, signatures, and many, many more, as you can see on this slide. But this is the first work that looks into forward security for updatable encryption. And this has not been achieved before. Let me briefly explain what updatable encryption is. It's a symmetric encryption scheme that has an additional feature to rotate encryption keys for outsourced ciphertext. So imagine, for example, you have your data stored encrypted on a cloud server, and now you want to change the key. What you can do is to download all your data, decrypt it, re-encrypt it, and upload it again, but that's very cumbersome. And updatable encryption gives you a more elegant way to do this. So key generation works for any symmetric encryption scheme and also encryption. But then you have this next key functionality that takes as input the key and outputs a new key together with an update token, this delta 2 here. And then there's the update procedure. So this update token can then be sent, for example, to your cloud server. And the cloud server can use this update method that takes as input the ciphertext and the update token and outputs a new ciphertext that can now be decrypted under the new key. And security is usual indistinguishability of ciphertext, and the adversary can choose the epoch and is given access to both keys and tokens as long as they do not trivially decrypt the challenge ciphertext. So even if you're changing the keys here, this does not give you forward security at all. And the reason is that the adversary can learn the update tokens in the security game. And so if your key does get leaked at some later point, an adversary who has access to the update tokens can decrypt all previous ciphertext, because he can just update the ciphertext to the epoch where the key leaked and then decrypt them. So this seems to be this is an inherent problem with updatable encryption. And looking forward, this work solves this by restricting the update functionality so that old ciphertext at some point cannot be updated anymore, even if you have the update tokens. So the starting building block of their construction is symmetric punctuable encryption, which is a tag-based encryption scheme with a very fine-grained forward security guarantee. So it has the usual key generation. Encryption now takes as input, along with the key and the message, a tag. and will output a ciphertext associated to this tag. And you have a puncturing method that takes as input a key and a tag, and then outputs a key that is punctured as at this tag, which means that this new key can no longer be used to decrypt ciphertext associated to such a tag, but it can still decrypt all ciphertext associated to different tags. And you can repeat this puncturing over and over again so that you can puncture your key at many points. And yeah, this gives you forward security because, for example, what you can do is that whenever you get a ciphertext, you decrypt it, and then you puncture your key at the tag of the ciphertext, so you kind of cannot decrypt it again. So if this key gets leaked at some point, it cannot be used to decrypt any ciphertext that you have received in the past. And security is the usual indistinguishability game. The adversary can choose the tag and gets access to punctured keys or to keys as long as they are all punctured on the tag of the challenge ciphertext. And a special case of this puncturable encryption is epoch-based puncturable encryption, where we no longer have tags, but instead we have linearly evolving epochs. And key generation will give us a key for the first epoch. And encryption now takes as input just a key and a message and will output a ciphertext for the same epoch as the key. And the puncturing now just takes a key and outputs a key for the next epoch. And the properties is, well, this new key, or here the key for the second epoch, can no longer be used to decrypt ciphertext associated to the first epoch. Note that here there's no way to update the ciphertext to new epoch, so that's the difference to updatable encryption. And this gives a very coarse-grained type of forward security. And yeah, in order for this to be useful, we need to make it more fine-grained. And this is why this work introduces tag-inverse puncturable encryption, or for short TIPE. So that's the main contribution of this work. So to define this and to give a construction of this. And the idea is to start with puncturable epoch-based puncturable encryption, but exclude certain ciphertext from the epoch-based puncturing, and also to add expiry epochs. So concretely, as before, key generation gives you a key for the first ciphertext, but encryption now also takes as new inputs a tag and an expiry epoch. The tag has nothing to do with the epochs. Key puncturing, as before, takes as input a key and outputs a key for the next epoch. But optionally, you can now also provide some tags. And for each of the tags you provide, it will output a token. And this token can be used to exclude the ciphertext from puncturing. More concretely, there is this exclude puncturing procedure, which takes as input ciphertext and such a token. And the token has to be for the same tag and the next epoch. And then it will output a new ciphertext for the next epoch, and tag and expiry epoch remain unchanged. And the guarantee is that this new ciphertext can now be decrypted under the new key as long as the expiry epoch has not been reached. So yes, security is the usual indistinguishability of ciphertext. The adversary can choose here the epoch, and he can also get access to keys and tokens as long as they don't give them a trivial win. And maybe this already looks a bit like updatable encryption, and it is indeed it's this kind of updatable encryption, but with additional features. So the key puncturing is more or less our update key mechanism. These tokens are the update tokens, and the exclude puncturing procedure can be seen as a way to update the ciphertext. So they construct tag-inverse punctual encryption, and this in particular implies updatable encryption with expiring ciphertext, which is a forward secure variant of updatable encryption. And updatable encryption with expiring ciphertext also implies plain updatable encryption. This works by setting the expiry epoch to something exponential in the security parameter so that it will never be reached. And the security notion they define for updatable encryption with expiring ciphertext also implies the CPA security notion for plain updatable encryption schemes. And when you plug in the construction they have for tag inverse punctuable encryption and use this as a plain updatable encryption scheme, they also get the first backward leak updatable encryption scheme with sublinear ciphertext from standard assumption, which solves an open problem posed in 2 recent works. And I don't have time to go into the technical part, but let me just say that they use dual system groups, which have been used previously to achieve adaptivity for IBE schemes, for example. And yeah, it's interesting to see them now in the context of updatable encryption. Okay, so let me summarize. Forward security is an essential security feature and for many cryptographic primitives. And this works looks into forward security for updatable encryption and therefore introduces tag inverse punctuable encryption. And yeah, this is quite a versatile cryptographic primitive. And yeah, an interesting direction to look into is whether this can be used for other applications than updatable encryption. Thank you.
Can you ask questions instead of the authors?
Yeah, I think it would be better if you send questions to the authors. I'm not sure if I can answer.
Okay.
Thank you.
Okay, let's speak again. Thanks. The last talk of this session is combinatorially homomorphic encryption, and Ear is going to give a talk.
Thank you. Okay, this talk is about homomorphic encryption, and it's going to work with Yuval Ishai and Ron Rothblum. So homomorphic encryption, introduced by Rebbe Stadelman and Dirtuzos, is a general idea of an encryption scheme that allows computation over the encrypted data. Intuitively, it means that given a function f and an encryption of x, we can efficiently compute something that behaves like an encryption of f of x. It is a very useful notion with many applications, such as online voting and outsourced computation, and also many instantiations over the years. However, when we try to formally define it, we stumble upon a number of issues. For example, requiring the scheme to support the evaluation of every possible function turns out to be very hard to achieve. And on the other hand, supporting the evaluation of a single function can be trivially achieved by any encryption scheme, and it is not clear where is the threshold. And also, another example is whether the output of the evaluation algorithm needs to be distributed like valid encryption, and if not, what is the requirement. So let's take a look at existing definition for HE. So in the HE world, we divide time into 2 periods, BG and AG, before Gentry and after Gentry. And before Gentry, when we said HE, we mainly refer to the linearly or additively HE definition, which is inspired by the algebraic notion of homomorphism. The plaintext and the ciphertext spaces are both groups, while the encryption algorithm is homomorphism between them. Now, the main issue with this definition is that it captures mostly number theoretic-based schemes, and in particular, it doesn't exactly capture lattice-based schemes that only support bounded number of linear operations. And also, it doesn't capture, of course, non-linear homomorphisms such as FHE. Since Gentry, the common definition uses the compactness property. Here we say that a scheme is homomorphic with respect to some fixed circuit class. And given a circuit from this class and the encryption of some x, we can efficiently compute something that can be decrypted to the output of the circuit on x. And the key property for non-triviality here is compactness, which roughly means that the size of the output of the evaluation algorithm is smaller than the size of the circuit representation. Now, defining HE this way also has a couple of issues. First of all, it brings us back to the question from the start of the talk, which is what circuit classes should we support? Supporting every possible circuit class is only an FHE, and moreover, there are many HE schemes that only supported bounded, doesn't support every possible circuit class and still found to be useful. Also, it isn't clear what is the minimal notion of compactness. There are a number of different interpretations in the literature. And also, as you can see, this definition is model dependent, and questions that arise are, for example, why circuits, which circuits, and why not other models of computation. Okay, so our goal in this work is to propose a canonical definition for HE that will help base it as a standard cryptographic primitive. And we want the definition to be clean, minimal, and model independent. We wanted to capture schemes that are traditionally considered homomorphic. And we wanted to respect the relations between HE and other cryptographic primitives. And we propose to do it using, from the lens of a combinatorial measure, and specifically communication complexity and visit dimension, but mostly communication complexity, and this is what I will focus on right now. So a quick introduction to communication complexity. The setting is that we have two parties, Alice and Bob, and we have a function and input distribution. An input pair is sampled, and Alice gets X while Bob gets Y. And now Alice needs to send some message to Bob, and Bob needs to output f of xy with high probability. Now, there are no secrecy requirements, so the trivial solution is for Alice to just send her entire input. However, for some function, she may be able to send a shorter message, and the communication complexity of the function over the input distribution is the minimal number of bits Alice has to send so they can compute the function correctly with high probability. Okay, now for our HE definition, so given a private key encryption scheme, we say it communication complexity homomorphic or CC homomorphic if it is semantically secure. So this excludes, for example, textbook RSA. And if there exists some function and some efficiently samplable product input distribution, such that on the one hand, computing it requires C bits of communication, but on the other hand, if Alice and Bob are both computationally bounded, and we give Alice an encryption of Bob's input, and we give Bob the secret key, then they can compute it using less than C bits of communication, less than the lower bound of the standard setting. And I will call this setting the homomorphic setting. And also we can adapt this entire definition to public encryption. Okay, so we have a definition, and we believe it's clean and minimal, and it is model independent. And so the first natural question is whether it captures schemes that are traditionally considered homomorphic. And so our first theorem is that any linearly HE scheme is in fact CC homomorphic, and this captures, for example, Goldwasser-Micali and Gamal, Paillier, Regev, and more. And as a theoretical example, we will prove at the same time that any scheme that is homomorphic with respect to the OR function over binary input is also CC homomorphic. So we use the inner product communication complexity problem over random vectors. And for the second theorem, we use the same function, but with a different input distribution, where Alice gets a random binary vector and Bob gets a random unit vector. This is an example of how it is sufficient for us to find even a specific, very tailored-made input distribution that works to instantiate as definition. So it is a known result in communication complexity that computing the function over both of these input distribution requires omega n bits of communication. However, consider the following protocol in the homomorphic setting, where Alice is given bit encryption of Bob's input, and she homomorphically computes the inner product function, which of course she can do with the linearly HE scheme, but she can also do it with the OR homomorphic scheme over this specific input distribution. And now Bob can decrypt it, and since Alice sent only a single ciphertext, then the communication of this protocol is less than the lower bound of the standard setting, and therefore the scheme is CC homomorphic. Okay, so the next natural question is whether the definition respects the relations between HE and other cryptographic primitives. So we know that linearly HE implies public key encryption, collision-resistant hashing, and private information retrieval. And in the paper, we indeed show that CCHE also implies PKE, or moreover, lossy PKE, reproducing the result by Rothblum. And assuming additional natural requirements, it also implies CRH, reproducing the result by Shah et al. And a stronger but closely related variant we present in the paper called VCHE implies P, reproducing the results by Cauchy-Levy-Ostrowski. Now, the fact that we need slight variations of the definition to get the different primitives seems inherently required to us. And also, it kind of distills the minimal notion of HE that each of the primitives needs. Okay, so let's take a look, for example, on a non-interactive key exchange protocol that can be used to construct a PKE scheme. And this is a generalization of a Rothblum construction. So we start with a private key CCHE scheme with respect to some function and input distribution. And by the CCHE definition, there exists a protocol in the homomorphic setting for the function. So now the receiver samples an input for Bob, Y, and a private key K, and he sends the public key Y and the encryption of Y. Now, this seems absurd. Like, why would you encrypt something and then reveal it right away? It seems like not very useful. But in fact, it is useful because now the sender can sample an input for Alice, X, and he can send the message of Alice from the homomorphic protocol on X and the encryption of Y. And now both parties can compute f of xy. The sender can do it directly, while the receiver can do it using Bob and the message from Alice. And f of xy will be the agreed secret. For security, we first switch from the regular public key to a lossy public key by replacing the encryption of y by the encryption of independently sampled y prime. And now, assuming towards a contradiction that the adversary can predict f of xy given the transcript, we can construct a protocol in the standard communication complexity setting that will break the lower bound, which is of course impossible. So the protocol will use shared randomness that we can eliminate later. The parties will use it to sample identical encryption of some y prime. And Alice in the new protocol will use Alice from the homomorphic protocol to generate a message to send to Bob. And by the CCHE definition, this message is shorter than the communication complexity of the function. Now Bob can use the adversary to predict f of xy. And again, since this protocol breaks the lower bound, it cannot be correct, and therefore the adversary cannot be correct. Okay, to show the versatility of the definition, we also show in the paper that it captures schemes that are not traditionally considered homomorphic. For example, encryption from low noise LPN. And this requires a different set of parameters for the CC game, namely a weak correctness. And therefore, we get PK and CRH, but we don't get peer in this weak correctness regime. And this produces recent result for low noise LPN, but we believe it does it in a conceptually simpler way. Okay, so for summary, we propose a new canonical definition for HE called CCHE. We believe it is clean and minimal, and it is model independent. It captures schemes that are traditionally considered homomorphic, and it implies PKE, and the slight variations of it imply CRH and peer. And therefore, we propose it as a standard notion, a default notion for HE.
We have a lot of time for questions. Is there any question?
Hi. Hello. Hi. Thank you for the talk. So I was wondering, do you draw any relationships between the CCHE and the previous definition of HE, or is it just
yeah, so we
okay.
showed that linear HE, which is kind of the standard definition for HE, implies CCHE. And the default notion of HE currently, which is the second I showed with the circuit class, doesn't really define well because you don't know which circuit class the scheme is required to support. So the linear HE is the more well-defined definition, and it is implied CCHE.
Thank you.
Other questions? Okay, let's thanks the speaker again. This is the end of this session. Coffee break.
test.
Hi, everyone. Welcome to the session. The first talk is Memory Checking for Parallel RAMs by Surya Madhyalagan. I want to note this paper won the Best Young Researcher Award paper. So,
Hi. Yeah, thank you very much to the committee for giving me this award. This is so unexpected. Okay, so yeah, today I'll be talking about memory checking for parallel RAMs. And first, I'll give a quick TLDR of what this paper achieves. So first, we define a new notion of memory checking in the parallel RAM model. Then we construct some memory checkers in the PRAM model, which match the asymptotic efficiency of the regular memory checkers in the RAM setting, while also achieving optimal parallel depth. And finally, as an application, we construct a maliciously secure oblivious parallel RAM with polylog overhead. Okay, so what's the memory checking problem? So consider the problem where a client outsources the database to a remote cloud server. So now she outsources database and is trying to read to this database. But because the server might be malicious, these responses back might be incorrect. So if the client only has small but trusted local memory, how can she ensure the correctness of all these responses back from the server? Well, we're cryptographers here. The answer here is quite simple. It's just authentication. But this only works if the database were static. So what if the client is allowed to dynamically update the database? So for example, now she can also perform writes to the database. And now when she reads to the same address, she wants to read the most recent version of that address. So she needs to make sure that what's sent back here, for example, is data new and not data. So this is exactly the setup of the memory checking problem. So this was introduced by Blum et al. In 1994. So basically, a memory checker is a layer between a client and a server. So you can think of this as a program that's in the computer, for example. So now that the client sends its read or write operation directly to this memory checking program instead, then this memory checking program sends a bunch of read or write requests to the server and determines some response. So for the correctness property, we basically want to ensure that the memory checker either aborts or only sends back correct information. The correctness here, again, means that it sends back the most recent version of an address. The second property we want is completeness to make this non-trivial. So basically, if the server were honest, the memory checker should not abort. Okay, so this is the usual setting of memory checking, but it's actually quite natural to consider the setting where there's multiple users using a shared memory. So for example, again, you have many clients using the same database, or you have a computer with many CPUs using a shared memory, or even a distributed computing setup where there are many GPUs computing some algorithm together. And in this setting, it's actually very natural to also want integrity verification. So one thing I want to point out here is that there's actually more modes of failure. So for example, if you have two clients who make a concurrent write to the same address, so one thing a malicious server could do is actually branch this memory. So now there's going to be two versions of the server, and now when both these clients try to read back to the server server could send back data 1 to the first client and data 2 to the second client. So there's this issue of branching. So one thing I want to actually point out here is, maybe the server doesn't actually have to be a malicious server for this to happen. For all you know, this is just a confused server that just made an honest mistake. So you can also think of memory checking as a tool to ensure correctness, or almost like a sanity check tool. So so it makes sense to also want integrity verification in this setting. So yeah, just to illustrate what I mean. So for example, this branching problem that I mentioned, it could just keep happening and happening over and over until you have many different versions of the database. So in some sense, one of the main goals of memory checking in the parallel setup is to have a one consistent timeline or one consistent version of the database across all the clients. So this brings us to our definition. So in the memory checking for parallel RAM setup, you're going to have many clients, and these clients are going to make concurrent accesses. So first, because there's many different memory checkers now, we're going to allow for one setup phase. So in this setup phase, all these memory checkers for each of these clients sets up some key, for example, and initializes some state together. But after this, we're not going to allow any direct communication between any of the clients. And this is just to have a general framework for this. So maybe it's possible that the clients have some underlying secure channel, but I don't want to make any assumptions about this. So for now, we're going to say that none of these memory checkers can communicate after this setup phase. So concurrent accesses just means that at any time step, all of these clients can send a batch of queries to the server. And now the memory checkers in parallel are also going to communicate to the server and determine some response. Again, we want this correctness condition, but it's a little different this time. So correctness here means that, first of all reads are correct. So again, that means the most recent version of an address. The second property we want is that if there were concurrent writes made to any location on the server, exactly one of them is accepted. So we're going to give the adversary full power here. So I'm even going to say that the adversary gets to pick who wins, but only one person can win. So if you're familiar with the PRAM setting, this is actually the arbitrary CRCW setting of computation. So it's arbitrary concurrent read, concurrent write. So again, we have a completeness condition that says that if the server is honest, then none of the memory checkers will abort. So what do we care in terms of efficiency? So first, we want the amount of space stored by each of these memory checkers to be small. So for this talk, think of it as maybe storing some counters and maybe an authentication key. So this will be O of 1 words or maybe O of lambda bits. The second thing we care about is storage size. So how much space the online server needs to hold. And again, in this talk, we actually achieve O of 1 blow up. So think of O(n) words. So now we care about work blow up. So think of work blow up as the ratio of the number of arrows in the second part between the memory checkers and the server to the ratio of underlying concurrent accesses. So how much more communication do you need to conduct to support a parallel set of requests? And finally, the most interesting metric to me, at least, is the depth blow up, because this is the parallel RAM model. So we have some parallelization capabilities if you want to make use of. So how many steps of computation do you need to execute all of these arrows in between the memory checker and the server? So we want to also minimize the number of rounds of communication you need to conduct. Okay, so this brings us to our results. So first, just to recap what we know in the regular RAM setting, the best known constructions have O of log n work blow up, and this was already shown in Blum et al. And there's also a lower bound of log n over log n communication for some special cases, which most constructions fall into. And this is a result by Dwork et al. So immediately, if you serialize a given PRAM algorithm by just saying at every time step, only one person can talk, this actually gives you O of log n work blow up, but it gives you O of m log n duck blow up. So you're really not using the parallel capabilities. So the main difficulty in trying to take these existing constructions and making it parallel is that all these constructions have this tree structure. So you can think of, for example, a Merkle tree. So when you're trying to make any updates to the database, you might end up with many collisions when updating the internal nodes of a given tree. This is the main difficulty in parallelizing this algorithm. But nevertheless, in this work, we show how to obtain O of log n depth. So assuming one-way functions, we show a memory checking protocol for PRAM programs with O of log n worst case work and depth blow up. So that means every single, to support any single query, any server only has to make log n communication, needs to send log n requests to the server. Okay, I just want to make a point here that is actually shown that this one-way function assumption is essential for memory checking. So if you want memory checking with sublinear overhead, you need one-way functions. And this was shown in a work by Nauer and Rothblum. So as an application of this, we'll consider the oblivious parallel RAM model. So you can think of an OPRAM as a access pattern hiding PRAM compiler. So it's like a memory checking compiler type setup, but the goal of this compiler is to hide the underlying access patterns. So there's a beautiful recent work of Ashraf et al., which shows that in the honest but curious setting, you can actually achieve overlog and blow up in both work and depth for OPRAM. And this is in fact optimal, as they show in Ashraf et al. And oh, I guess I forgot to mention this, Larson and Nielsen in 2018. Okay, so as a corollary of our previous result, we actually obtained the first construction of maliciously secure OPRAM with polylogarithmic overhead. By directly composing our memory checker with the existing OPRAM construction, we obtain a maliciously secure OPRAM compiler with overlog squared n work and depth blowup. The asterisk here is just to say this is not actually worst case because the underlying construction is not worst case. Okay, and the third result we have is that assuming one-way functions, we show an offline memory checking protocol with O1 amortized work and depth blowup. So what is offline? So in the offline memory checking setting, we're going to allow the client to send many batches of requests to the server and do this many times. But during this query phase, the server is allowed to lie. And the memory checkers are allowed to send back incorrect responses. But at the end of the day, there'll be a verification phase where the the memory checkers communicate with the server and determine if whether all the responses back from the server were correct or if some mistake happened. So this is a much weaker guarantee. You just have to figure out if something wrong happened somewhere, but you don't have to know where it happened. So in this setting, basically the construction adapts this counting technique for offline memory checking from a previous work with Nikon. So basically the high level idea is this. Each of these memory checkers is going to store a local counter, which basically counts the number of updates that particular memory checker made. Now you're going to tag every single database entry with a counter of how many times that database entry was updated. And in the verification phase, all we're going to do is check if these two sums are equivalent. And we basically set up our algorithm in a way such that this is actually sufficient. So here's a high-level idea of what happens. So this is the setup. So again, all the database entries are tagged with the number of times it was updated. And every single memory checker contains the number of times it has made an update. So now let's say these three memory checkers are trying to write to the same address. And they're all like, hey, pick me. So now if the server were honest, it will pick one of them arbitrarily to win. And the rest of them will get back a signal that their write did not succeed. And now what memory checker 1 is going to do is, because its write succeeded, it's going to write back to D4 with incremented counter 4. And it's going to also locally increment its counter. So both of these are going to be incremented. And it's easy to check that this summation of counter I equal counter TJ is going to be maintained. So this equality is going to be maintained. But there are two main types of attack the server can still do. The first is this sort of spoofing attack. So basically, when all of these memory checkers try to write to D4, it can pretend that none of them actually won. This violates our correctness condition because we wanted exactly one of them to win if there were concurrent writes. So in fact, it's interesting because this type of attack will not happen in the regular RAM setting, because if you're the only person writing and you say, I want to write to this address, you know you will win. So this is very unique to the PRAM setting. So to catch this attack, somehow it almost feels like authentication is necessary. And basically, to deal with this, we basically come up with this quick agreement protocol to ensure that someone has to win this in this setup, so the spoofing attack should not happen. The next is the branching attack, which I've already mentioned before. So now maybe the server says, okay, 2 of you actually won, but they don't know this yet. But the point is that, well, each M1 and M2 both locally increment the counters, but because they're both writing back at the same time to this D4, they can only increment counter by 1. So somehow the left-hand side is only incremented once, but the right-hand side is incremented twice. And because we're authenticating all of these writes, the server is not able to artificially inflate the counter values on the server. So therefore, all you have to do is basically check this equality to see whether the server lied at any point. This is a very quick, high-level overview of the offline checking algorithm. Okay, so I wanted to leave you guys with some open problems. The first, can we obtain a statistically secure offline memory checker for CRCW programs with O1 amortized overhead? So again, to motivate this, before I mentioned there was a spoofing attack, and that seemed to be the main reason why we needed authentication. So at least in the single RAM setting or in the PRAM setting without any concurrent reads or writes, we know how to achieve this. But I don't know how to get this in the case where there are concurrent reads and concurrent writes. The next question I have is, can we use these memory checkers to obtain an optimal maliciously secure OPRAM with OV login work and depth blow up? So in a previous work, we actually did this for the ORAM setting. So that means in the single client setting by interleaving offline and online memory checking with the existing ORAM constructions. The question is, can we do the same? Okay, thank you very much.
Any questions?
Over here. Can I ask for the online memory checking problem, is the login blow overhead in the depth, is that essential? Because if I think about a hash tree, there's no depth blow up. You just know, you can ask all the questions in parallels.
Yeah, so I think there needs to be, because when you're sort of like aggregating it over the tree, you need to do it level by level so that you can catch any like, so if a subtree is updated many times, you need to catch it at that root of that subtree. And it feels like somehow you need to do each level at a time to make sure you can somehow collate all this information without too much blow up. I don't know if that made sense, because a subtree could be updated many times. So it feels, I couldn't get around this. It felt like I had to do each level of the tree separately. But that's a great question, whether you can do this all in one shot somehow. Maybe you can get better depth blow up if you, I don't know, for example, allow many, like a MCPU underlying algorithm, but maybe like 2 MCPU memory checking algorithm. Maybe it's possible.
Thanks. We'll take other questions offline. Thank the speaker
Thank
again.
you.
Okay, so the next talk is near optimal private information retrieval with pre-processing by Arthur Lazzaretti and Babis Papamanthu, and Arthur will give the talk.
Hello. Yes. So thank you, Tal, for the introduction. Right, so this is near optimal private information retrieval with preprocessing. And we'll start by just defining all these terms in the title. Oh. Okay, it seems like not the best with this click. All right, so this private information retrieval, introduced by Coratal and then a series of other works, is this protocol between client and server where the client is given as input a number between 0 and n, we call it x. The server is given an input n-bit string called db, and they exchange a message, after which the client outputs the x bit of db. And for this protocol, to satisfy our privacy requirement, we say that there has to exist some simulator A star that can act as the client. And the server cannot tell if it's interacting with this client, the real client, or A star. Okay, so this is private information retrieval, and it's been used as a building block for many different privacy preserving applications. Metadata hiding messaging, private movie streaming, private ad serving. However, all of these run into a sort of fundamental bottleneck with respect to their non-private counterparts, which is server computation. And this turns out to be, as we defined PIR before, inherent in that PIR, as I defined, requires O of n server work. This was shown by Baimao, Ishai, and Malkin in the early 2000s. And so this sort of motivates the study of PIR with preprocessing. And specifically in this work, we're going to consider client preprocessing, where the client and server interact in a preprocessing phase, after which the client stores this hint of size sublinear in n, which it then uses as advice to perform a series of queries. Okay, and so this is our model. And what we show is that in this model, we construct a scheme that can achieve O of square root of n is server computation, amortized, O of 1 bandwidth, and O of square root of n client space on a single server, where these O's are squiggly O's, they're approximate O's, they hide polylog and lambda factors. And this is improved upon improving on previous work from Shiata and Crypto 21, which showed the same asymptotics on 2 servers, or by Koring and Gibbs et al. In Eurocrypt 22, which showed similar asymptotics but with larger bandwidth. And I will also mention here that there has been some concurrent work that achieved these same asymptotics from different techniques, and that was presented in Eurocrypt 23. Cool. So our results can kind of be summarized in 2 large blocks. So first, we construct some pseudorandom sets, which I'll define, with the following properties. These sets have a concise representation. So you can represent this set with a key that's much smaller than the number of elements in the set. You can enumerate this set, I guess I skipped the membership test. So you can check if an element is a member of the set fast, in time also much smaller than the set size. You can enumerate the set, again, fast. Here, fast means time proportional to the set size. And the special property of these sets is this adaptability, which means that it supports adding and removing a constant number of elements from the set while maintaining the concise description. Along with this adaptability, we're also going to need this extra property, which is the resulting key also hides to an adversary which elements were operated on. Given a key that, for example, had an element added to it, it cannot tell which elements out of the elements in the set was added afterwards. Cool. And then after this, we show that we can use these pseudorandom sets with special properties to achieve the peer with the complexities that we wanted. So for this talk, I'm going to just mainly focus on 1, and I'm going to have to refer you to 2 for our paper for number 2. And I'll just start by saying that Xi et al. In Crypto 21 achieved such sets that had a concise representation, fast membership testing, fast enumeration, with supporting 1 removal in the way that we want. And we extend it here to support a constant number of additions and removals. Cool. So our starting point is the privately punchable PRF primitive, which is just a tuple of 3 algorithms produced by Bonnet et al. And then follow-up work by also Bonnet et al. And Canetti and Chen. So it's gen, eval, and puncture, where gen and eval are just standard PRF algorithms, and the puncture is special in the following sense. So this puncture algorithm, for the purpose of this talk, we'll define as follows. It's going to take in the original PRF key and a set of points, a set of p points, and it's going to output a punctured key where the outputs for the points that we input to the puncture algorithm are re-randomized. So we basically, this key reflips the coins. The puncture algorithm reflips the coins for the points that we input and outputs this key, which hides which elements were reflipped. So this was shown to be possible from LWE by the works that I said it before. And so using this, we're going to construct sets of approximately square root of n elements in 0 through n-1, picked from some sampling distribution. And our initial attempt is as follows. For each x in 0 through n-1, we're going to say that x is a part of the set defined by this PRF key k, if and only if f of xi colon equals 1 for all I in 0 to log n over 2. And this definition could be a lot to wrap your head around at once, but a simple example makes it pretty clear. So if we take n equals 16 and we generate a privately punchable PRF key, let's try to check membership for x equals 7, which can be represented in bits as 0, 1, 1, 1. So all the definition is saying is that x is in the set if we evaluate the x and it evaluates to 1, and then we evaluate x without the first bit and it also evaluates to 1, and then we evaluate x without the first 2 bits and it also evaluates to 1. So this is the whole set definition with respect to the key k. And we can see at first that this distribution already satisfies at least concise representation because we represent the set with just the key. It also achieves fast membership because just by definition, we can test membership of a given element in O of 1 time, where this, again, O is squiggly. For enumeration, it's not so clear that we can enumerate this this set in time proportional to its size. So this set is going to have size square root of n. But by definition here, we're defining it per element. So naively, we would have to check each element in 0 through n minus 1. But if you'll notice here, if we start from the bottom and check smaller strings first, so if we start by the strings of size log n over 2, and let's say that 1, 1 evaluates to 0, then we never have to check 3 and 7 and 11 and 15 because they all share this initial small bit string in their membership testing. So building on this idea, we can construct a fast enumeration algorithm that enumerates the set also in O of square root of n time. Cool. So what we wanted initially was concise representation, fast membership testing, fast enumeration, and adaptability. Let's look at where we are right now. We have sets with a concise representation, assuming that this PRF key is small. We have fast membership testing by definition. We hand-waved fast enumeration, but we're going to have to settle for that because we want to get to adaptability. So how do we add and remove elements from the set while hiding which elements were removed? And you might get a hint that it's going to use the only property of the PRF that we haven't used yet, the puncturing. So to remove an element from the set, all we do is we take Z to be the set of, okay. Some technical problems. Thank you. So we take Z to be the set of points that define X's membership, and we just puncture this key, initial set key at Z. What this gives us, if you recall the definition of the set, is that with very high probability, we're going to remove this X from the set because we need all this set of points to evaluate to 1, and if we re-randomize them, then very likely one of them is going to flip to 0. And also by the puncture property, we get that this new key hides which element was operated on. However, what we get is also an undesirable property, is that with some small probability, we either do not remove this element or we remove other elements from the set because of that property of sharing evaluations that we looked at before. And in the paper, we show that we can actually handle this quite easily by just appending some extra points here to be a part of X's membership evaluation. And for adding, we use a similar idea, except we use some rejection sampling. We just run this puncture algorithm until we get a key which has this X inside the set. Okay? And this sort of assumes that this privately punctured PRF puncture operation is re-randomizable, but Canetti and Chen show that this is possible from LWE. And so what we get again is that this always adds elements to the set, albeit in potentially a large amount of time, expected square root of n at time, and in the paper we show how to get this down to O of 1. The punctured key, again, by the privacy property on the puncturing, is indistinguishable from a key picked from the keys that originally contained X. And again, we run into this problem with the dependency, which we say we can deal with. Cool. So what's left to show is we have shown how to either add an element to the set, or remove an element from the set. But we do not know how to make these work together or to make this work for many times. And the idea here is quite simple. We just use C of these privately punctured PRF keys, and we define our set just slightly differently, where membership is defined given a set key K, which is a group of keys now. Membership is just defined as XORing the evaluation at these K keys at the same points. And now we can define additions and removals sequentially on each key one at a time. And we show that this satisfies the appropriate notions of correctness and privacy. So that sort of concludes our building our pseudorandom sets, modulo some details. And for number 2, I'm just going to have to refer you to the paper. Thank you very much.
Thank you. We have time for questions.
Yeah. So what is the best known lower bound on client space for sublinear server computation?
Right. So I forgot to mention that, but Corrigan, Gibbs, and Kogan in 2020 show that this square root of n computation and square root of n client space trade-off is optimal. So if you, for square root of n online server time, you can get at least square root of n client space in this model. So the model assumes that the server does not store any additional bits at the server other than the database.
If I just aim for sublinear server computation, not necessarily square root n, then is there?
Then right. So it's sort of a sliding scale that multiplies to n.
Okay.
Does that make sense?
Yeah.
We can actually achieve this with this work as well. I just fixed this trade-off to make it simpler.
Okay. Thanks.
What would it take to get it under other assumptions? Do you have some nice abstraction of, I mean, you have an abstraction, but it's quite complex. Can you reduce it to, I don't know, some kind of programmable homomorphic secret sharing, or have you thought about abstracting what you need from LWE here?
I see. Well, so right. So this pseudorandom set is the abstraction. It's not clear that we need LWE specifically for this. Yeah, I'm not sure what exactly we would need to abstract away from the LWE. I do know that what we didn't show here of the construction is that the online phase also requires some FHE in order to get these sets to work sort of obliviously, and that's, I think, the main bottleneck right now.
Okay, yeah, thanks.
Thank you. Okay, so the next talk is Proactive Secret Sharing with Constant Communication by Brett Hemingway Falk, Daniel Noble, and Tal Rabin, and Daniel will give the talk.
Thank you very much for that introduction. So I'm first going to present what proactive secret sharing is. I'm then going to explain why doing it with constant communication is somewhat of a big deal. And then I will present in detail one of our protocols that achieves this in the semi-honest setting. And I'll give a little bit of intuition for our protocol that achieves this in a malicious setting. So what is proactive secret sharing? So normally in MPC, we're used to the setting where we have the adversary is able to corrupt some fixed portion of nodes, but corrupts these at the beginning of the protocol, and they're set throughout the protocol. And this is a good model in many situations, but sometimes we have a situation where corruptions is a bit more like a disease, that the adversary is able to periodically corrupt different devices and keeps corrupting various devices, compromising them, learning their secrets, causing them to behave incorrectly. But also periodically, the devices are able to be refreshed, that the adversary is kicked off of a device, maybe the device is rebooted, maybe a new device is used to replace this device, maybe credentials are reissued. And therefore, the adversary, while they are eventually able to corrupt each member of the system, will only be able to corrupt a certain fixed portion at any given point of time. So this is the mobile adversary model, and security against it is called proactive security. So specifically, we're looking at proactive secret sharing. That is, we want to be able to share a secret in such a way that even if the adversary is able to corrupt m out of n parties in each epoch, they will never learn the secret. So this is a brief summary of previous work in this area. And essentially, every protocol up to this point required order n communication for each refresh phase. That's n communication per participant. Some protocols were able to kind of get around this by batching this. So if L was a batch size, they could have order L, N over L communication per party per batch, per item in the batch. But sometimes you're not really able to batch secrets. So for instance, if the secret is a private key either for encryption or signing, that is just one set of data. It's not really able to be batched. So ours is the first protocol that's able to achieve proactive secret sharing that's sublinear, and in fact, we're without batching, and in fact, we're able to achieve it with constant communication. So today I'm going to be presenting a protocol that is secure against a passive adversary, and it again has constant communication, and it achieves a linear threshold in corrupted parties. I'll also give a little bit of intuition about our protocol that's secure against an active adversary, which again requires constant in-end communication. There's a kappa term for because it involves PRFs, and it has a lower threshold of square root n adversaries, parties that can be corrupted per round. So I'm going to be making extensive use of this tool in mathematics called expander graphs. Specifically, I'm going to be looking at bipartite balanced expander graphs of constant degree. So let's break that down. So bipartite means there are two parts and edges only exist from one part to the other. So I'll call these the left and the right parts. Balanced means that each part is of equal size. So in this particular graph that I picked, each part is of size 7. It's constant degree. That is, each vertex has a constant number of edges. In this case, that's 3. And now the property of it being an expander is the kind of crucial one that we need to describe. And specifically, I'm looking at the vertex expansion property. So that means if we pick some set on the left and we look at all of its neighbors, and therefore the corresponding set on the right, there is some expansion that has happened. So the set on the left was of size 2, the set on the right is of size 5, and so there was an expansion of 5 over 2. The set has kind of increased by a factor of 5 over 2. So this expansion amount is one amount that we care about, and specifically we would want this amount to be greater than 1, so there has actually been expansion. We also care about how big the set can be and still have expansion. Clearly, for instance, if the set on the left was containing all of the elements, you couldn't have any expansion because the set on the right is the same size. So specifically, the graph on the left, you might think I've just picked 2 very nice vertices that have good expansion, but actually if you were to pick any 2 vertices on the left, they would expand to 5 vertices on the right. So this graph has the property that as long as 2/7 of the graph on the left of any 2/7 of the nodes are selected, they will have expansion 5 over 2. So these are these 2 terms that we care about, alpha and gamma. Now, you might think that I picked this particular graph because it has this good expansion, and I in a sense did pick a particular graph. This graph does have a name. It's called the Heward graph. And if you feel like interested in discrete math, you can look up its relationship to something called the Fano plane. But the general properties that I've described actually exist for all values of n. This was a series of very interesting works by Spielman et al. Showed that for any value of n, if you have you can have a constant degree expander or a constant degree bipartite graph that has expansion some constant greater than 1, and that this is true for some constant portion of the graph. So there are relationships between the terms d, alpha, and gamma, but these terms do not depend on n. This is kind of surprising if you think about it, that you can expand each vertex just as a constant number of neighbors, and regardless of what set you size for any that you choose for any constant portion of the graph, you will get this constant expansion. So this is the critical property that we need. And now I'm going to show how we can achieve proactive secret sharing using this technology. So the way that we're going to do this is we're going to additively divide the secret. So the sum of the SIs is equal to the secret S, and each of the SIs is chosen randomly. And the way that we reshare is that each party additively shares its own share, and so we get shares of shares, and they send that to their neighbors. So explaining a bit more, the vertices on the left correspond to parties, and the vertices on the right also correspond to parties in the subsequent epoch. So they kind of we kind of assume that there will only be a certain portion corrupted in the left and a certain portion corrupted on the right. So they secret share their shares, obtain shares of shares, and then the way that you combine to get the new shares is you simply add up the shares of shares that you received. And some basic math shows that the total is maintained. So what about privacy? So I'm going to show that in this particular graph that you can tolerate up to m adversaries. So I'm doing it with small constants just because it's easier to illustrate, but all of these will hold true for constant proportions, and that's the proof in the paper. But I'm basically going to follow through almost the same proof in the paper, but with small constants. So I'm going to show actually that now the adversary can corrupt M in any round, but it's possible that they might learn more secrets than that in a particular round. So if they controlled all of the messages that were sent to someone else, then they know what share that person is going to achieve. But I'm going to show that they will never actually learn this for more than 5 of the parties. So we can show this by induction. So clearly in the first step, they can only corrupt 3 parties, and 3 is less than 5. So they only know the secrets of at most 5 parties. And so there are 2 parties that they don't know the secret of. And now I'm going to show the kind of inductive step of the proof. So since there are these 2 parties that are uncorrupted and their secrets are unknown, also the shares of shares that they send are going to be unknown. And so the parties that receive shares of shares from those parties, those shares of shares will completely randomize the secrets. And so the adversary doesn't know these secrets that are constructed. The adversary may corrupt 3 of these 5, but there will still be 2 of these 5 that have not been corrupted. And so this property that the adversary knew the secrets of at most 5 out of 7 parties is maintained inductively. So yeah, this is the proof, and the proof in the paper is basically the same, except it's constant proportions. Cool. So I'll give a little intuition for the robust protocol, and so we can use kind of the same idea to achieve something that has robustness but no privacy. So clearly this protocol has no robustness. If a single party sends an incorrect share of share, then the secret is changed and robustness is lost. What we can do instead is have a protocol that only has robustness and no privacy. So this isn't really a secret sharing protocol, but it's kind of a value maintaining protocol that if the adversary is able to corrupt a constant portion of the nodes in each round, they're not able to change this value. So the expander graph also has this this property that even if we say that the majority, so if we have a majority of good nodes on the left by some constant fraction over a majority of good nodes on the left, then a constant fraction will have the majority of their neighbors be good. And so this means that we can have a protocol with linear corrupting a constant portion of malicious nodes that still maintains robustness. And then basically we can kind of combine these 2 protocols where each of these parties in the privacy setting is replicated using the robustness protocol, and therefore we're able to have square root n privacy and also square root n robustness. It's a bit trickier because you have to make sure that the replicas have the same randomness for their proactiveness without leaking. Anyway, it's a bit more subtle, but the details of that are in the paper, and I encourage you to read that. Thank you, and I'll take any questions.
Questions?
So these expander graphs, are those explicit or?
Yes, they can be explicitly constructed and actually constructed in polynomial time.
Okay, thanks.
Any other questions? Okay, let's thank the speaker again.
Thank you.
So the last talk of the session is Improved Polynomial Secret Sharing Scheme by Amos Baimel, Oriol Faras, and Or Lastry, and Or will give the talk.
Thank you for the introduction. So I'm going to talk about improved polynomial secret chain scheme, a joint work with Amos Baimel and Oriol Faras. So I'm going to start with a high-level overview before going into the definition. So secret chain scheme is a useful tool in cryptography. Linear secret chain scheme are useful for applications, but less efficient. Polynomial secret chain schemes generalize linear secret chain schemes to a higher degree. And according to the best known secret chain schemes today, we know that linear secret chain schemes are less efficient than degree 2 secret chain scheme, less efficient than general secret chain scheme. So the question that we ask in our paper is, does the share size decrease as the degree of the polynomial grows? And the answer is yes. So the tool that we use to construct those polynomial secret chain scheme is a conditional disclosure of secret, CDS protocol. Okay, so now I'm going to continue to definitions and some background, starting with secret chain scheme, which was introduced by Shamir Beckley, Ito Seto, and Ishizeki. So in secret chain scheme, we have a set of parties and a dealer D. We also have an access structure, a collection of authorized sets. For example, gamma K, all the sets of size K or more. The dealer holds the secret S, creates random shares, and distribute them to the parties. We say that the scheme is correct if every authorized set, i.e. a set in the structure, can compute the secret from the shares. And we say that the scheme is secure if every unauthorized set cannot learn any information about the secret. So the share size of secret chain scheme, in this talk, I'm only going to refer to secret chain scheme of 1-bit secret. We denote the length of SI as the share size of party I, and the share size of the scheme would be the maximum share size among all parties. And the main goal would be to construct schemes with small share size for general access structure. So polynomial secret chain scheme, before going to the definition, let's see some motivation. So a secret chain scheme is linear if every authorized set can reconstruct the secret using a linear function. Most non-secret chain schemes with small share size are linear. And we also have a good exponential lower bound for the worst access structure for linear secret chain scheme of n to the n over 2 from Babaga and Wilkerson. For general secret chain scheme, the situation is a bit different. So the best known upper bound is 2 to the point 585n from Baimel and upper bound and near. And the best known lower bound is linear omega of n over log n from sigma. So there's an exponential gap between the upper bound and lower bound for general secret chain scheme. So we want to ask two questions. The first is, can we construct efficient nonlinear scheme for a broader family of access structures? And the second is, can we extend the lower bounds for a broader class of secret chain scheme? And we also want to obtain insights for general secret chain scheme. So again, a good candidate to achieve these goals would be polynomial secret chain schemes, since it lies between linear secret chain scheme and general secret chain scheme. So now going to the definition, polynomial secret chain scheme was introduced by Paskin, Chernevsky, Vedun, and then by Baimel, Tomar, and Peter. I'm going to refer to the definition of Baimel, Tomar, and Peter. So as I said before, is a generalization of linear secret chain schemes to higher degrees. The shares are vectors over some field F of size L. A set of parties, authorized set of parties of size K, for example, reconstruct the secret from the shares using a reconstruction function. In our case, the reconstruction function will receive K vectors of length L and will output 1-bit secret. And we call this secret chain scheme a degree D polynomial if for every authorized set, the reconstruction function is a polynomial of degree D. For example, if D equals 1, then for every authorized set, the reconstruction function is linear, therefore the scheme is linear. Okay, so now I'm going to show a toy example for a polynomial secret chain scheme. So let's say we have two parties, and the access structure will be the set of the two parties, also called 2 out of 2 access structure. The dealer used 3 random elements to create the shares. And these would be the shares that it creates. Each consists of 2 field elements. And the two parties together will be able to reconstruct the secret using the following reconstruction function. So looking at the last monomial, you can see there is a polynomial of degree 2, which variables are the coordinates of the shares, which makes this scheme a polynomial of degree 2. Okay, as I said before, we use conditional disclosure of secrets, CDS protocols, in order to construct a secret chain scheme. So CDS protocols was presented by Gartner, Ishai, Kushilevitz, and Malkin. In CDS protocol, we have K parties, also called the servers, and we have a referee. We also have a function f from n to the k 201. Each party has a private input xi, and the parties also know a secret s. In our case, also would be 1-bit secret. So the goal for this for the parties would be to disclose the secret to the referee based on the condition of f, meaning that if x1 to xk is 1 input of f, we want the referee to learn s. Otherwise, if it's a 0 input of f, we want the referee to learn nothing. So each party sends one message to the referee, but in this state, it would be a difficult goal to achieve since f relies on k independent inputs and the parties cannot communicate between each other, so they also hold common randomness. So in this talk, I'm also going to refer to polynomial CDS protocols, which means in this context that the referee reconstruct the secret from the messages using a polynomial function. Okay, so now I'm going to present our result. I'm going to present the results, the main result regarding secret chain scheme. So as I said before, we showed as the degree of the reconstruction grows, the share size decreases. So more formally, every n-party archi structure can be realized by a secret chain scheme where the degree D reconstruction and share size n to the 0.585 plus some constant CD times n, where the constant is order of log D over log D. So comparing that to the previous results, the best unrestricted general secret chain scheme with unrestricted reconstruction have share size to the 0.585 n, and you can see comparing that to our results that our results approaches to the best unrestricted result as D approaches infinity. The previous best known polynomial secret chain scheme was of degree 2, prior to our work was of degree 2, and share size to the 0.705 n. And there wasn't a result for a general degree D reconstruction. So first improvement that we show in our work for polynomial secret chain scheme is secret chain scheme with reconstruction degree of 243 and share size to the 0.673 n. Our second result regarding K-service CDS, so we show that for every D and every function f, there is a degree D K-service CDS for f with the communication complexity n to the k-1 times constant CD, where the constant is the same as before, order of log D over log D. So again, comparing to previous results, the best known K-CDS with unrestricted reconstruction have communication complexity of n to the O tilde of square root of k over log n. The best known polynomial CDS prior to our work was of degree 2 with communication complexity n to the k-1 over 3. And again, there wasn't a construction for a general degree D for K-service CDS. But there is a lower bound for K-service CDS with the degree D reconstruction from Bamel to Mann-Peter of omega of n to the k-1 over D plus 1. So looking at the lower bound compared to our result, you can see there wasn't a way for us to avoid the k-1 factor in the exponent. The only possibility for improvement would be in the constant CD. And again, first improvement that we present for polynomial K-service CDS has a reconstruction degree of 243 and communication complexity n to the k-1 over 4, which improves the degree 2 communication. Okay, so now I'm going to show high level of our construction, a very high level of our construction. I'm going to show the construction flow. First, before I'm going to show our construction flow, I'm going to show the construction flow of the best known general secret chain schemes, and I'm going to compare it to our construction flow. So all best known general secret chain schemes today start with a combinatorial structure called matching vectors. Using matching vectors, LVW relying on the work of Dvir and Gopi, constructed two server CDS. From two server CDS in subsequent work of LVW, they constructed K-server CDS. And then using the reduction of LV and Appelbaum Bemen-Peter, they constructed secret chain schemes from K-server CDS. So our construction flow starts with what we call sparse matching vectors, which are matching vectors with few non-zero entries. Then from sparse matching vectors, we constructed polynomial two-server CDS. Then from polynomial two-server CDS, we constructed polynomial K-server CDS. And then using the same reductions as before, we achieved polynomial secret chain schemes while preserving the reconstruction degree of the K-service CDS. So our contribution lies in those stages. We first define and present construction of sparse matching vectors. Then we generalize the construction of the two-service CDS of LBW in order to use the property of the sparsity to achieve polynomial two-service CDS. Then we generalize the construction of the K-service CDS to achieve polynomial K-service CDS while preserving the reconstruction degree from the polynomial two-service CDS. Okay, so now I'm going to show conclusion and some problems. So I showed in this talk two results. The first one regarding secret chain scheme. As the degree of the reconstruction increased, the share size decreases and approaches the best known general secret chain scheme. And it's the same for K-service CDS. As the degree of the reconstruction increase, the communication complexity decrease with the same constant order of log D over log D. So these two results with the known lower bound for polynomial K-service CDS raises two obvious open problems. I want to talk about the third open problem. So our generalization of the two-service CDS gives us the option to enable us to use what we call S1 matching vectors, where S1 are a large set compared to the previous used matching vectors. And from that, we can obtain a better two-server CDS and two-server pre-protocol for general reconstruction, not non-polynomial. Okay.
We have time for questions.
So all these lower bounds and upper bounds are in the information theoretic setting, right?
Yes.
And is it like what is known in the computational setting? Like, do we know of better lower and upper bounds?
Okay, for this I'm less familiar.
Okay. Thanks.
Any other questions? Okay, let's thank the speaker again. And the business meeting is at 4:35. Please come, everyone is welcome.
Hi, a couple of announcements. There is an extra bus from the HSSB and the venue and to the dinner location. So it will be 5:05, 5:15, and 5:20. And there would also be a third bus coming back from the dinner venue. Like all three buses will leave at the same time. So we have a few spare T-shirts. And those who wish to obtain them should show up tomorrow at 8:30 at the registration desk, and first come, first serve. And we don't have any extra larges left. And we don't have at the moment any spare an entire set of souvenirs. And however, anybody, I mean, the souvenirs of anybody who doesn't show up by 10 o'clock, the last day of the conference, will be handed out also at the registration desk. Yeah, so anything else? No, okay, so that's it for now.
Okay. I think so. Yeah, like this. This is. Okay. Hi everyone. Let's start. Welcome to the business meeting of TCC 2023. I'm Tal Malkin. I'm the head of the steering committee. So this is the plan. All of these bullets will not take too long. I will give some comments from me. Then we will announce TCC 2024. Then we will have comments by the general chairs and comments by the PC chairs. And then we will open the floor for discussion. We have some topics in mind, but also if you have any topics you want to discuss as a community. Okay, so here are my comments. This is a cut and copy and paste of the IACR Code of Conduct. I just wanted to remind you that you all signed it to register for the conference. I wanted to encourage everybody to be aware of the Code of Conduct and also to point out the points of these points of contact are people from the webpage of the IACR as well as the general chairs of this program. Kaimin and Boyin, you can approach any of these people. You can also approach me if you feel any issues. I will try to help you. Okay, so I just wanted to point it out. Okay, so this is the Theory of Cryptography conference. The steering committee consists of the following people: Jesper Bus-Nielsen, Hujia Rachel Lin, Yuval Ishai, Krzysztof Pieczak, Manoj Prabhakaran, Salil Vadan, and myself. Here in this conference are present Yuval and Manoj and me. You can talk to any of us about any TCC related issues, or if you want to volunteer to host TCC at your institution in the future, that would be awesome. Come talk to us. Okay. So the program chairs for TCC 2023 are Guy Rothblum and Hotek Wee. Hopefully you know that by now. We wanted to say thank you to both of them. We have some beautiful plaques for them. Okay, so we are thanking Dr. Guy Rothblum for serving as program co-chair for TCC 2023 on behalf of the entire steering committee. Don't go. We'll do a picture in a minute. Okay, we're also thanking Dr. Hotek Wee for serving as the program co-chair for TCC 2023 on behalf of the steering committee. I don't know if it's on. Yeah, it's on. So the general chairs, Kaimin Chang and Boyin Yang, really did an amazing job, as we are all enjoying. If any of you, I'm sure none of you are still hungry. Everything is wonderful. The setup, the food, the talks. Thank you very much. So we have plaques for you. Beautiful plaques. Okay, so the IACR Theory of Cryptography Conference, thanks Dr. Kaimin Chang for serving as General Co-Chair for TCC 2023. And also thanks the IACR Theory of Cryptography Conference, thanks Dr. Boyin Yang for serving as General Chair for TCC 2023. Oh, I forgot the thank you. And I also want to present the TCC 2023 Best Young Researcher Award. This award goes for the best paper authored solely by young researchers, where a young researcher is a person that at the time of the paper submission is at most 2 years past his or her graduation from a PhD program. So this year it actually went to a person who is in the PhD program. Surya Madialagan, are you here? So the ISCR Theory of Cryptography Conference awards the Best Young Researcher Award in TCC 2023 to Surya Madialagan for the paper Memory Checking for Parallel RAMs. All right, this was the most exciting part, I think, the awards. Oh, I guess this part is also very exciting. I forgot, all the parts are really exciting today. So I want to announce TCC 2024. Alon, get ready. So the program chairs will be Alet Boyle and Muhammad Mahmoudi. The general chair is Emanuela Orsini, with some help by Alon Rosen and Luca Trevisan. And Alon will come say a few words about the location, which you can already see on the bottom there, and the dates. Thank you for hosting.
Don't thank me prematurely. Yeah, don't thank me yet. It's only next year. Okay, so the next TCC, 1 year from now, December 2 to 6, is going to take place in marvelous Milan. The venue is going to be Bocconi University, in particular the business school. It's the building that you see here on the right. Traveling to Milan is pretty convenient. It's a central hub, and many flights into Europe go via Milan, many flights every day. Between 40 and 50 million travelers just in Malpensa airport every year. What do you get in Milan? You get to see art, fashion and design, particularly fashion and design, as you can see on me. Nightlife, Alps and lakes, and Italian food. And looking forward to welcoming you next year.
All right, this clicker, I think. Yeah, so the next thing we'll have comments from the general chairs and then comments from the program chairs. So I think that's it for me in official position. So Boin, you wanna come? Your slide is next, the slide you sent me.
So we managed to break almost even on about 110 grants, and there is 172 registrants. I mean, a lot of them are from Taiwan because they've never been to an international crypto conference before, and they took the opportunity. And the next largest contingent is from the USA, and I mean, there are many people from many different countries, and we are glad that many people made it here despite being in the war zone. We have 78 students, and the other 94 are regular. And we have a affiliated workshop called PQCSM2, and 74 people attended, and they included some early career talks from like TCC attendees. And this is an on-site conference, except for those who are totally unable to come. And we gave out 30 stipends of various sorts. So I hope everybody liked it so far, and you will enjoy the rest of it. So thank you.
Okay. Okay, so just picking up on Boyan's report, I wanted to start on a personal note. I feel that I have to speak, say something about the situation in Israel. So first, maybe particularly for us, most relevantly, there were several members of our community who wanted to attend the conference and couldn't because of the war, including at least one student. So I just wanted to say that they're in our thoughts, and so we can all think of them and of all the innocent. Speaking for myself, on a personal note, thinking of them and of all the innocent people who were affected by the horrific attacks in Israel and by the war. And I just hope the suffering ends soon. And picking up on Iftach's talk yesterday, that all the kidnapped hostages are returned safely to their families. Okay, so that ends my personal note. And from now on, we are the program chairs and we have a report on how things went. So my illustrious co-chair, Hotek, and I have been debatably either colleagues or friends since first meeting at TCC 2006 at Columbia. So this is an inside, also an inside joke from TCC in Zurich, whatever year that was. So yeah, TCC has been a really important, meaningful conference for each of us on our own and for both of us together. I also remember, as a reward for making this great friend in TCC 2006, I was immediately asked to do a big favor for Hotek, not so big. I needed to submit his thesis for him. So, there are things you gain when you go to TCC. Okay, so a little bit about the conference. I learned to use Excel. That was something interesting that I learned from being a program chair. So comparing with previous years, we had a good number of submissions for TCC 2023. A serious uptick from 2022. So these are the number of submitted conference to in each of the last 5 years. In blue, we have the number of accepted papers. So 68 accepted papers, which is a 40% acceptance rate, sort of in line with what's been happening since 2020, which is significantly more than the acceptance rate beforehand. And maybe we'll talk about that later in the open discussion. So the program committee for TCC 23, you see here, thank you very much to all of the program committee members. We had 39 PC members, a little bit less than previous years, but sort of more or less in line. In terms of the makeup of the PC, we tried to be diverse, both in terms of the seniority level of the PC members, also in terms of gender diversity and geographic diversity, and we tried to factor diversity in every way that we could. We did as well as we could. Hotek, you want to say something about the timeline?
Sure. So here's the timeline in the call for papers. Right, we have a June for submission deadline, a rebuttal phase, and the notification dates. And things went a bit better than expected. By like a few weeks before the rebuttal deadlines, we have about half the reviews. And as soon as rebuttal started, we had all the reviews in. So I want to thank the PC and the sub reviewers for doing such an excellent job. And we continue to stay ahead of the deadline by sending the notification out 1 day early. A bit about those reviews. We have roughly 3 reviews per paper, 4 for PC author papers and borderline papers, more or less.
each PC member reviewed roughly 14 papers. This is slightly higher than the load for TCC 2022 because we have a slightly smaller PC and a larger number of submissions. And altogether, we have 526 reviews and 25 papers with, in fact, more than four or more reviews. In general, the sub-reviewers were, the best case was when the sub-reviewers were experts on the subjects and the PC members continued to stay involved during the discussion. The medium PC member delegated about half of the reviews, and we were able to get a lot of participation during the discussion phase from the external reviewers. We also have a small mini rebuttal, somewhat useful, also mostly just to sort of make sure that scheduling and everything's in place. I want to say that our PC members were amazing. They definitely deserve the A+, apart from, right. So I also want to acknowledge that our reviewers and the PC members were extremely diligent and thorough in their reviews. Along the way, they discovered 3 critical bugs, 3 medium severity bugs, and many smaller bugs. And most of the smaller bugs were resolved during the rebuttal phase or through email exchanges with the authors. Right. One interesting thing this year is that in some sense, accidentally, we invented a new field of meta complexity for TCC. So in particular, we received unsolicited reviews of the TCC reviews. And these unsolicited reviews look a bit like this. I have to say that this is one of the best review rebuttal processes I've been a part of. I think the paper in particular, its presentation improved significantly through it. And this is from an accepted paper. We also have an unsolicited review from a rejected paper. I've never seen a review this long and with so many good details. We need more reviewers like this. And even beyond the TCC reviews, we also have this additional unsolicited review. And I'll let you guess who this came from. And this says that the quality of LaTeX submission by TCC authors was much better than crypto authors. Maybe because they don't imagine themselves as much as programmers rather as writers.
Me? Okay. It's okay. Yeah. So the program was single track, 65 slots. Since you're all paying very close attention, you know that there were 68 accepted papers. So there were 3 merges, 15-minute slots. The merged papers get a little bit longer since there are 2 people speaking. We really wanted to stick to an in-person conference with in-person talks. So there were a few exceptions, but they were all under truly exceptional circumstances. And only exceptional circumstances. And this was the format. It's very similar to what we had last year. There was a disruption in the TCC format for COVID, and now we've been doing this, which is similar to what was last year. I think we should discuss the format, so I think we'll do that in the open discussion phase. I have something to say or ask about that. We had 2 invited talks. Iftach Heitner gave an excellent talk yesterday, and Zvika will give a talk tomorrow, so stay tuned for that. You want to take over for the gratitude portion?
Sure. Special thank you to the following people. Of course, our amazing TCC 2023 PC. Let's give them a round of applause. Here they are. And our 197 external reviewers. Many of whom I think are also in the room right now. And right, definitely to Tal Malkin and the TCC Steering Committee, past TCC PC chairs for their advice and wisdom. All of you and all the authors who submitted their work, the invited speaker, Iftach and Zvika, all of you as conference attendees, session chairs from the PC and volunteer session chairs. Kevin McCurley and Kay McCurley, these are the IRCR webmaster and volunteers who manage all the logistics stuff. And once again, from the both of us, a special thank you to our local chairs, Kamin Chong and Poing Yang.
So I'm commandeering the open discussion, but Tal, you are in charge of it. Anyway, I'll start. Yeah, we'll discuss it and then we'll move back to Tal's slides. So, okay, going back. Oh, there's no slide, so it's open discussion. Great. So yeah, I told you about the format. So we ended up having 65 slots for accepted papers, which means that there are 12-minute talks for the papers and a couple of minutes for transition and questions. I think it's a question about how well it's working. That we had a big discussion. We had a serious discussion about it with the steering committee. Some people feel that this is a good format, that the short slots sort of are enough to give you sufficient detail about papers you're interested in. And if by chance there's a paper you're not interested in, which is very rare, hopefully at TCC, then it passes quickly. However, both now, we're up to whatever 68 accepted papers, 65 slots, and certainly looking forward, TCC is growing. We hope the community is growing. So there's a question on what we want to do, and something has to give, right? So either we can have either fewer papers accepted or maintain this number of papers as the number of submission grows. Which means a lower acceptance rate. Now, it's not unprecedented. So, 2019, there was about a 30% acceptance rate. 2023, we have 40%. I think our feeling was that we didn't accept papers that should have been rejected. So, and I don't know. Yeah, I don't like the idea of lowering personally the acceptance rate, but others may feel differently. So it's an open discussion. We can keep the talks, at this length or shorten them. Or one option following other conferences in other areas is to have a mix of short and long talks. So we can have some highlight talks and then shorter presentations and poster sessions. For the bulk of the papers, we can think about going dual track. I do want to say right off the bat that we all feel that TCC, one of the really nice things about TCC is that we are a small community and TCC brings us all together. There's something about going to dual track that feels like it would change the nature of the conference and the community. There is a possibility of doing partial dual track. So maybe for some areas we could have dual track. Or if you have better ideas, other ideas, we'd love to hear them. So anyway, that's just a call to open up a discussion if anyone has anything they'd like to say. Maybe Tal can start. It wasn't an open discussion, it was a monologue discussion.
Yeah, Guy summarized everything, but there are obvious pluses and minuses to all of these things. So I kind of, even if it's obvious, I want to hear your opinion about what should get more weight out of the pluses and minuses. Like, for example, going to a mix of short and long talks, or poster or not poster, that's like a two-tier system or more than 2 tiers. Is that a problem or is that okay? What about dual track? Somehow I would love to hear your opinions, even if Guy already said it, because the hard thing to decide is what to give more weight to, and that really depends on the community. And I want to acknowledge the people here are the people who managed to come. Oh, one other thing, did you mention about the TCC has traditionally been very, very, and still this year, very, very in person. One could also consider supporting, this is maybe, I don't know if it's really related, or it's a different topic, supporting more, allowing and encouraging and supporting more remote talks. But that's maybe a different type of topic. Anyway, so please, yeah, just speak up. Amos.
Of course, I have something. Before the conference, I thought that 12-minute talk would be bad. I think it's working, but we shouldn't go lower than that, and we shouldn't higher the acceptance rate. I would reduce a little bit the acceptance rate and have 4 or 5 longer talks.
Reduce the acceptance rate and have 4 or 5
and
longer
slightly reduce the. We have 4 days and we have full 4 days. We cannot, if you will have longer talks, we won't have. I would have 60 accepted papers, something like that, and have at least the best student paper award should have been longer, and maybe a few more highlighted talks can be longer. People even can write it in the CV that longer talk.
But not parallel track.
Parallel tracks, I don't see any way logical to have parallel that people won't be interested in being in 2 places in the same time. There's no logical way. Practice more theory, we will all be in the ferry track.
Shai, you want to say something?
That one.
You
Yeah.
can also just talk without me calling on you.
So I think that the main feature of conferences and TCC in particular is to bring many people together and have them meet in person and interact. I think that longer talks and longer breaks are important, and I think it's worth it even if you need to switch to parallel sessions. Yeah, that's pretty much it.
So I agree with both Shai and Amos, even though they contradict each other. So I think lowering the rate a bit is sensible. I think we should not take for granted that the community will grow. It's not clear that this is the trend. So we need to see what's happening. And I think simple is good. So different lengths of talks and different tiers is not a good idea. TCC is characterized by simplicity, and I think it should stay this way.
So do you agree with Amos that parallel tracks are bad and with Shai that parallel tracks are good?
Yes.
Yeah, please speak up. You know, honestly, we had this discussion last year as well.
Actually,
It's
I'm
never so
interested
clear
to
what
hear
do.
the young people because it's important for
Yeah.
for TCC that we hear the young people.
I-
So any young people here
Yeah.
that have an opinion,
Yeah, young people. We can do a raise of hands, but maybe somebody has a comment. Yeah, please.
I want to ask if it would be a possibility to make TCC one day longer if the community is growing and we decide not to lower the acceptance rate. Would that be an option?
I guess that's another option to make it longer. There's also always an issue with traveling for longer. Fewer people can come. Sometimes there are family responsibilities, teaching responsibilities. Both of these tend to be older people's problem, but yeah, but it's an option. Yeah, I mean, in general, as the steering committee, we let the chairs decide what to do, but we still want to hear from the community and decide. Yeah, so that's another option.
I'd like to say that the one priority I'd like is just the longer talks if possible. I don't know which things to reduce for that, but like that's one thing I like.
Yeah, I guess good talks should be longer and bad talks should be shorter, but it's hard to know in advance. You can be voted off the island. Yeah, Alex, you wanted to say something?
Yeah, I understand wanting to encourage in-person talks as much as possible, but personally, I don't really understand the point of talks by proxy speakers. I don't know, kind of just seems a little bit like a waste of time to me.
Okay, that's like I brought this point up about in person or not, but I feel like it's a slightly different discussion from this. So I'll get back to it in a minute to that point about in person or not. It's an important point on its own. So, I see. Okay, who thinks double track is an acceptable solution? Just non-committing show of hand. Alon, you can vote twice. Who thinks a double track is an acceptable solution? Okay, and who thinks it's not an acceptable solution? Yeah, okay, it's about the same. Alon voted twice for the first one and once for this one. Same number. Yeah, hard to know. Okay, should we switch to the topic of in-person versus remote? Alex, I think the reason for the proxy is not so much that it's better than remote, but it's to really, really discourage authors from assuming they can give a Zoom talk. Because this is really not good for the authors. This is I don't know, I didn't arrange for this, so I'm answering from my imagination. I may be wrong.
We actually thought that the experience of having an in-person talk, even if not by the authors of the paper, is better for the audience. I I think we had an exceptional setup here this year, which we weren't an exceptional physical setup. Like we have a really, really large screen, and we could see the speakers who are giving remote talks pretty clearly. So I think that's a lesson for the venues in the future. But our main consideration was actually, when there was at a late point, people wanted to give a Zoom talk. Our main consideration was for the audience at the conference, and having this character of an in-person conference.
Yeah, so the whole in-person versus allowing remote talks is a whole other topic that's, I think, on one hand, I'll try to summarize the point. TCC in person is very, like Shai said, the point is to come together, to meet people, for younger people, to meet older people, and for older people to meet old friends, etc., and colleagues. But on the other hand, many people cannot come, for various reasons, including family reasons, teaching reasons, like I said before. Hopefully there will not often be political war reasons. So it's not clear. There's some, in the past, different chairs. As I said, the steering committee allows the chairs to take a big role in deciding what to do. Some chairs in the past were really, really, really cared about in person, others were less so. I'm not sure. I personally, in my personal opinion, we need to either try hard to be very in person or give wide support. Like we can't be in the middle. Like doing half in person, somehow, that's my opinion. And I love the in-person aspect, but I acknowledge that it's problematic sometimes.
So let me just say something real quick. This is more, from a personal perspective. Maybe it's useful to keep in mind what our sense of what the role of TCC is. So it came up sort of maybe the more senior member of the committee can correct me, but it was sort of a sort of around the topic of theoretical foundations of cryptography and about a community and bringing people together. This is always a very much a major role in this role, major part of its existence. And over the years, I think there may be people who think of it as a good conference, a very strong conference that's just below Crypto Eurocrypt. If you think of it from that point of view, then maybe you think of it as Crypto Eurocrypt grows, TCC should scale accordingly. But I don't quite think of it that way. I really think of it as first and foremost about a particular community. Of course, if that community grows, then TCC should grow. But if that community stays more or less stagnant while the rest of cryptography grows, then it's from my point of view, it's really more about Crypto Eurocrypt to accommodate the growth of the entire community, and TCC should still say its cause as serving a specific community.
So I disagree with two things you said. The first major disagreement is that you said TCC is below crypto and Eurocrypt. He meant above. He meant above. Okay, so we agree on that one. And the second one, I think that the conference serves a dual role, and there's a tension, right? Like on the one hand, I think the primary purpose of the conference is to be a scientific meeting for the community where we all learn about and exchange ideas and we form connections and collaborations. And this is the primary purpose of the conference, and I think it is served well by a small conference. On the other hand, the conferences in computer science have a role as a publication venue, and we can't ignore it. And in particular, students who are working on theoretical crypto need to have a place to publish. And this is, I assume, part of why TCC was created. I don't know, some of the more senior statespeople can chime in. And I think for that, if the TCC community grows and there are more students submitting good papers, the papers should appear, I would like for them to appear in TCC. So, yeah.
Yeah, so I don't know, any comments about allowing in-person versus, this is not exactly what you talked about. I mean, any comments about anything would be fine. I have one more quick topic that's separate, but it will be very quick. But let's finish this topic yet. Any other comments? Alon, what do you think about in-person versus remote?
I hate Zoom.
Yeah, I personally too, I like always plan and never succeed to listen to talks on Zoom, honestly. But, okay, Shai, yeah, please.
One more thing. Thinking after something that Otek said, Right. I mean, we're scientists. We get paid to travel and to various places and things. Presumably, society wants us to advance science. That's sort of the main goal of the conference. And on that level, I think that in person, having many people in person way exceeds the value. What gives them a lot more value than listening to talks. I mean, we have other ways of communicating ideas. Sometimes you get some new thoughts by listening to a talk to something that you didn't think about it, but other times you read and things. So I think having people in-person communication is the focal point of why we.
I mean, I would call for a show of hand, but I think this is a very biased sample of people who came in person. Maybe not. Yeah. Okay, I have a different topic. Anybody else wants to talk about these topics so far? My last topic is short. It came up in the past about options of possibilities of co-locating TCC with other conferences, such as Fox, DISC, CCS, that are related, sister conferences. I just wanted, and again, this is great because you can interact with people from this other community. So by the way, the TCC in North Carolina was chosen to be in North Carolina because Fox was going to be North Carolina. It was going to be a first time of a co-location with Fox. And then there was COVID, and this was even worse, that they both were at the same time over Zoom. But anyway, we can try again to co-locate in person with Fox, for example, or with other conferences on the other ends. I just wanted to get a feel. You are the people who came in person. Is it easier? Is it good to have two conferences? That would mean more days related to your question before. It would be longer. Not TCC. TCC will not be longer, but the two conferences would presumably not be fully overlapping, but somewhat overlapping or right after each other. It's harder to travel for longer. So this I did get this was discussed in the past, and I had an answer, a feeling from the community. I can tell you what it was, but I wanted to ask this current community, including younger people or everyone. Any thoughts, any pros or cons? Would you be happy if it's co-located with, let me say, Fox or CCS, because those are like on the two extreme, right? CCS is a security conference, Fox is a theory conference. Would you be happy if it's co-located with one of them? Unhappy? Depends which. Okay. Would one of them make you happy? What about rotation? Yeah, so the sense I got last time when we discussed this is that people would like co-location occasionally, but not always. Because there's also something nice about the intimate, this is our community thing. But I don't know if people, so to me, it sounds like we were gonna pursue in the steering committee, we're gonna try to pursue co-location on occasion, sometimes with Fox and sometimes with other conferences, yeah. But any comments about that? Yes, please.
Okay, sorry. I think, okay, I think it's just important to acknowledge like why this would be good. Uh, there are a lot of community, and I'm going to talk about DISC, not Fox and CCS, because
Sure.
DISC is like a quite a small community, much like this community, and I think that many times these small communities could like gain a lot by meeting each other, and I also think it's good if it's not every time, but some of the time. So personally,
One argument in favor of not co-locating is that it gives us more flexibility to hold it in places like Taiwan and India and other places. And I think it's important for people there to get exposed because a lot of them don't have a chance to attend conferences often.
Yeah, we really, I think we've been doing really well in terms of, and thank you to all the people who volunteered, in terms of locating in very different kinds of places. Yeah, I hear that. Any other comment? Okay, anybody wants to bring up anything else?
One
Yeah,
short comment.
please. I don't see where you are, but
You're at the back. So I just wanted to say that if two conferences that would potentially be of interest for many in the community take place in the same place, for some people it might be a problem in terms of visas. because unfortunately some people cannot go or have a hard time getting a visa, and two conferences take place in the very same place, they might not be able to go to either of them.
Okay, so is it fair to say that the common, you would agree, even those who said things against, like you and you, that it might be a good idea to co-locate with some regularity, but not too often, maybe every 3 years, whatever, right? Okay. Anybody want to say any other? These are topics that came up in the committee's work, in the steering committee's work. But if the community has any other comments that you want us to think about or take to the steering committee, please speak up. Okay, so I think that concludes the business meeting. And I don't know what time it is, but there are 3 buses to the dinner venue. So, like Goin said before. Thank you, everyone.
Yeah, as Tao said, the buses are waiting outside, so we can go to the banquet now. And the banquet will locate in the 5th floor of the building. The bus drop you, so go up to 5th floor to find the banquet location. Okay, see you there.